Welcome to SerPros. In this video, we're going to be looking at 4 network devices. These are hubs, bridges, routers, and switches. Okay, first we'll look at a simple hub. A hub's job is to connect devices in your network together. Let's see how it works. Let's say host A sends some data to host C. When a hub receives the data, it repeats it out of every port except the receiving one. Host C gets the data, but so does host B and D, so they simply discard it. The hub has many downfalls. It wastes bandwidth, as we've seen when host B and D receives unwanted data. A hub uses something called half duplex, which means it can't send and receive data at the same time without causing a data collision. This would cause your data to become corrupt and need to be sent again. So in overview, a hub is a layer 1 device, meaning it has no knowledge of addresses. All it does is repeat any data it receives. They have one collision domain and uses half duplex. This means it can't receive data and receive data at the same time. They waste bandwidth by sending data to hosts unnecessarily. It has security risks because all the hosts receive everyone's data. A malicious user could steal this. Hubs are old technology. They have now been replaced by switches, which we will take a look at shortly. Bridges were introduced to combat some of the shortcomings of hubs. They're used to segment networks into smaller sections. When data reaches the bridge, it decides whether or not to forward the data. It does this by looking at the destination and source MAC address. Every time the bridge receives data, it learns the source address, looks at the destination address, and decides to send the data or discard the data. We will look at this process in more depth when we discuss switches next, as it uses a similar process. So, a bridge is a layer 2 device. This means it can understand and learn MAC addresses. It segments LANs into smaller sections. It has 2 collision domains. This means data can be sent or received on each section of the network at the same time. A bridge usually has 2 ports. Bridges are not used anymore. They have also been replaced by switches. Now let's take a look at switches. Think of a switch as a hub and bridge rolled into one. It connects the devices together, but it can also learn which ports connect to which hosts. Let's see how this works. A switch has something called a MAC address table. This table will list each MAC address and which port is connected to. In this example, host A will send some data to host C. The switch receives the data, but as you can see, the MAC address table is empty. The switch in this case will forward the data out of each port just like a hub. Unlike a hub, the switch now learns host A's MAC address can be reached on port 1. When host C sends data back to host A, the switch knows exactly where to send the data. Now if you notice, the switch has learned that host C's MAC address can be found on port 3. Using this process, very quickly a switch can learn how to reach each host connected to it. Let's review. A switch is a layer 2 device. Like the bridge, it can learn MAC addresses, which are known as layer 2 addresses. A switch can use full duplex, meaning it can send and receive data at the same time. This means each port has its own collision domain. This is a huge improvement over a hub. Because it can learn MAC addresses, a switch saves huge amounts of bandwidth. And now because only the destination host is receiving the data, other hosts can't steal it. Routers. You can think of routers as the doorway out of your internal network and into the outside world. To understand what routers do, let's take a familiar example. Let's say this is your home computer, this is your switch, and this is your router. Now just on a side note, usually a home router has the switch built in, but in an enterprise network, their separate devices. So on the other side of the router, you have the internet. Let's say you send an email or visit a website. Your computer will send data to the router using its IP address. The router will then forward the traffic out of your home network and into the wonderful world of the internet. When data comes back, the router will forward the data back to your computer. A router is the way out of your internal network. A router uses not only MAC addresses, but also IP addresses, which means a router is a layer 3 device, because IP addresses are known as layer 3 addresses. It usually has 2 ports. A router is highly configurable and has many different features that are beyond the scope of this video. That's it for basic network devices. You've learned about the older hubs and bridges, and also the modern standard of switches and routers. I hope you've enjoyed this video. If you did, don't forget to subscribe, leave a comment, and give a thumbs up. Thank you for watching.
Hey, what's up guys? Welcome to Certbros. In this video, we're going to be getting started with probably the most valuable and important network study tool, Cisco Packet Tracer. If you're new here, this channel uploads regular IT training videos just like this one. So if you like what you see here today, don't forget to leave a comment, subscribe, and give it a thumbs up. So what is Cisco Packet Tracer? Packet Tracer is a network simulation tool designed by Cisco that gives you the ability to go out and build and design your own computer networks. Not only that, but it gives you the ability to visually play with networking technologies and protocols. It's an incredible study tool, and it's vital if you're taking your Cisco CCNA. But the best part, it's absolutely free. In this video, I'm going to show you how to download, install, and use this fantastic tool. So before we do anything, we're going to need to download and install it. To do this, we need to navigate to the Cisco Networking Academy website, which is netacad.com. Now, if you already have an account with Netacad, then go ahead and log in now. Otherwise, we need to go up to Courses at the top of the screen, then down to Packet Tracer. Cisco has an introduction course to Packet Tracer, which we need to sign up for before we can download it. So we need to scroll down here, and where it says Intro to Packet Tracer, click Learn More. So here is the course we need to sign up for, but we don't actually have to take it. We simply need to scroll down and click Sign Up Today. To enroll, we need to enter our details. Create account. Now we've enrolled, Cisco has sent us an email to activate our account. So this is the email we receive. All we have to do is click Activate Account. Once we do this, it's going to prompt us to set a password. So we'll just type in a password here and click Create My Account. So one more step is going to ask us for a bit more information, and we'll just fill that out very quickly. And once we've done, click Create Account. And finally, we have our account. Now from here, we could launch the course, but for now, we're just going to close this box. To download Packet Tracer, we now need to go up to Resources at the top, and then download Packet Tracer. This will take us to the download page. Now if we scroll down, we will see the installation options. So it does support Windows, Ubuntu, and macOS. We're running Windows, so I'm going to select the 64-bit downloader. Now Packet Tracer isn't a big application, but it may take a moment just to download. Okay, so it's been a minute or two and our file has downloaded. So we'll just simply double click onto that file and start the installation. Now I'm going to assume you've installed a program before, and essentially it's going to be a next install. Again, it's not a big program, but it will take a minute to install. And now it's done, we'll just click Finish and launch Cisco Packet Tracer. So when Packet Tracer opens, you're going to need to sign in. It gives you two options to do this, but we're going to select the Networking Academy login, which we just set up. So we'll just sign in with our credentials and enter our password. And we're in. So now we have Packet Tracer installed and set up. Let's take a look around. Now don't worry, I'm not going to go through every single menu and every single feature because I'll bore you half to death. But I will point out some of the most important features. The first bit we'll look at is the device menu. Down here in the bottom left corner, we have all of the devices that we can use. Across the top, we have the main categories. Across the bottom, we have the subcategories. And to the right, we have the available devices based on the category we select. There's also a search bar here in the middle. We currently have the networking devices selected. Under that, we have routers, switches, hubs, wireless devices, security devices, and wide area network devices as well. The next category is end devices. Here we have the normal devices you would expect, like PCs and laptops. But we also have some IoT devices which can be found under Home, Small City, and Industrial, and Power Grid. Another category that contains IoT type devices is the Components category. Here you'll find boards, LEDs, buttons, and more. Now the next category is a very important one. This is the Connections category. This is how we'll connect all of our devices together. Here we have connection types from straight-through cables, crossover cables, to coax and serial cables as well. Now if you're not sure what type of cable you should be using, don't worry, we also have an auto option as well. Now, to select a device, we simply choose a category. I'll choose Networking Devices, and then Routers. Then we just select the device and we can drag that onto the workspace. Or we can simply click on the device and then click where we want the device to be added. That brings us nicely on to the workspace. This is where we'll be building our network topologies. We have two options, the logical view and the physical view. What you see now is the logical view, which is where we'll be spending most of our time. But we can change to the physical view by simply clicking Physical at the top left. The physical view gives us a nice visual representation of the networks we build. You start off in the intercity view, and we can click down into the home city, even into the corporate office, and even into the wiring closet that we can see here. And if you look closely, we can see the routers we just added. The buttons at the top right allows us to navigate through the different levels. This view is great if you want to get a realistic view of how networks look and connect together. However, most of our time will be spent in the logical view. To go back to the logical view, we just need to go up to Logical in the top left corner. So let's take a quick look at the toolbar at the top. Here we have the Select tool for selecting devices, the Inspect tool, which is a way to see basic information like routing tables quickly and easily. We have the Delete tool, the Resize tool for resizing shapes, the Place Note tool so we can add text to our diagrams, and then we have some drawing tools such as the line, rectangle, ellipse, and freeform. The last tools are PDU tools, which allows us to add data to our networks for quick connectivity tests. Okay, so that is enough theory. Let's delete these routers that we have here and build our first network. So I'll click and drag to select the devices. I'm just going to hit delete on the keyboard. And yes, I want to delete my routers. So now we're going to need some devices. And I'm going to start off with some PCs. So I'm going to go down to the End Devices menu, and I'm going to select the PC and click onto the workspace. I'm going to add another one, simply click PC, and again, click onto the workspace. Now I want to switch to connect these PCs. So I'll go to Network Devices and select Switches. Now I could select a model here, but if you don't mind which model, you can simply drag from the subcategory onto the workspace. Great. Now we just need to connect these devices together. To do this, we need to go to the Connections menu. And in this case, I'm going to be using straight through copper cables. So I select my PC, choose which interface to connect it to. So this one is going to be Fast Ethernet 0. And then select it on the switch as well. Again, Fast Ethernet 0/1. Now remember, if you don't know which cable you should be using, for the time being, you can simply click the Auto tool, click the PC, and then click the switch, and it will automatically select the correct cable for you. So now we have our devices. What now? Well, we need to configure them. To do this, we just need to single click on each device. So I'll start with PC 0, single click, and it's going to open up a new window. On this screen, we get a visual representation of the device. As you can see here, we clearly have a PC straight out of the 90s, complete with what looks like to be a floppy disk drive as well. Here we can add and remove different modules. The available modules can be seen here on the left. If you click on the modules, you get a nice description at the bottom as to what they do. It's important to note that if you want to add or remove a module, you first need to power down the device. So, for example, if I scroll down and I take this Ethernet module and I try to remove it by simply dragging it to the left, it's going to give me a warning saying it can't be removed until the device is powered down. The way you would do that is simply by clicking the power button. Now, while this seems like a nice feature, trust me, once the novelty wears off, this can get pretty annoying. The next tab we have is the Config tab. Here we can configure some of the device settings, such as the display name, and some of the interface settings as well. The Desktop tab is where we see all of the available features for our PC. We have things like the command prompt, the web browser, email, lots of things here. But the one we're going to use is the IP configuration. Here we can set the IP address of this PC. So I'm going to set an IP address of 192.168.0.1. And if we click onto the subnet mask, it should auto-populate for us. Now we have the IP address, I'm going to do the same on the next PC. So I'll close this window down. Again, single click on PC 1, go over to the Desktop tab, IP configuration, and this time we're going to go 192.168.0.2. And again, auto-populate the subnet mask. Once we've done that, we'll just close this window down. Now we can also configure our switch, and this is really where the magic happens in Cisco Packet Tracer. So if we click on our switch, we get a new window. Again, we get a nice physical representation of the device and any available modules. If we click the Config tab, here we can make some quick and simple configuration changes. We also have the CLI tab, and this is where you'll be spending 99% of your time. This is where we interact and configure our network devices, which at the end of the day is why we're all here. We'll look at this more as we go forward, but I won't dive into this right now. The last thing I want to show you is probably my favorite feature of Packet Tracer, and that is the simulation mode. Simulation mode allows us to visually see messages being sent across the network. It's really a great tool when learning how protocols work and behave. The button to enable simulation mode is down here in the bottom right, and we just have to click Simulation. When we turn on simulation mode, this new panel appears. Here we can see each event as and when it happens. By default, every available event type is selected, which, if you leave them all on, you can quickly start to get overwhelmed by the number of messages being sent. especially when we start to build bigger networks. So what we want to do instead is to click the Show All/None button to deselect all of those event types. Then if we go to Edit Filters, we can select which type of event we want to see. For this example, I'm just going to go ahead and select the ICMP message type. Once I've selected that, I just close this window. And as we can see, only ICMP event types are selected. Now we have that selected, let's go over to PC0. And I'm going to open the command prompt. To demonstrate this, I'm going to send a ping to PC1. So I'll type ping 192.168.0.2, which is the IP address of PC1. And I'll press enter. Now I'll minimize this. And now we start to see these little envelopes. These envelopes are the protocol messages. We can click on the envelopes and get some information about the message. So on the first screen, we get to see some reference to the OSI model. But if we click onto the outbound PDU details, we get to see all of the information about this message. We can make this bigger. We can see the source IP address, the destination IP address, and then we see the ICMP message. This will come in very handy when we start to look at network protocols and how they work. We can close this message and then start to play the scenario through. So we could either hit the play button in the middle, or we can do it step by clicking the forward button. So we can see the message being forwarded to the switch then forwarding it to PC1, and we can see PC1's reply. Again, we can click on these envelopes and see the information being sent. If we click onto the details and expand this, we get to see the structure of the frame. Note the source IP address is PC1 and the destination address is now PC0. So this is the beauty of Packet Tracer. Not only can we build our own networks, but we can visually see how those networks and protocols are behaving. This will really help when it comes to solidifying these technologies. Of course, that was a very basic example of how Packet Tracer works, but you should now have the tools to go out and build your own bigger and better networks. This video is part of our full CCNA course, which can be found in the description. So go ahead and check that out. If you like this video, don't forget to give it a thumbs up, leave a comment and subscribe. The support from you guys really does help this channel grow. Other than that, thank you for watching. Wires? Who needs wires? In this video, we're going to be diving into the world of wireless networking. Here we have a couple of laptops and some phones. Now we could connect the laptops using physical cables, but many laptops don't come with Ethernet ports anymore, so that won't work. Of course, the phones definitely don't have Ethernet ports, so that definitely won't work as well. We may also want our users to move around freely without the need to plug into our network. The solution here is to use a wireless network. So how exactly do we do that? Well, first we need something called a wireless access point, also known as a WAP, or simply NAP. This access point is the center of our wireless network. Our laptops, phones, and other devices will then connect to our access point through the air and form our wireless network. So here we have a very basic wireless network. This is known as a basic service set, or BSS. This is where we have an access point connecting multiple devices, which are known as members of the BSS. Now there is a downside to wireless networks like this, and it's one I'm sure you've experienced before at home. When connected to a wireless network, you are restricted to the area the access point has signal for you to connect. And this signal area is known as the Basic Service Area, or BSA. Okay, great. So this is what a standalone wireless network looks like. However, most wireless networks will want to connect back to the wired network. The upstream connection from the access point that connects back to the wired network is called the distribution system, or DS. Now we can even use different VLANs for separate wireless networks if we want to. For example, we may have a wireless network called guest, and this is using VLAN 10. We might also have a wireless network called corporate, which uses VLAN 20. For this to work, we connect our access point to our switch using a trunk port, and the access point will take care of the VLAN tagging. Now let's look a little bit closer at how our devices connect to the wireless network. The access point is periodically advertising the network details using radio waves. These advertisements are called beacon frames. Any device within range is able to see these frames. Beacon frames contain several bits of information, but the two main bits are the basic service set identifier, or BSSID, and the service set identifier, or SSID. The BSSID is a unique identifier for the wireless access point, and it's based on the MAC address. You as a user will not see the BSSID, but it's important for our devices to identify the correct access point. The next piece of information is the SSID. Now the SSID is something I'm sure you've seen and used before. It's essentially the wireless network name. So when you go into a coffee shop, hotel, or even a friend's house and you ask them what is the Wi-Fi, that name that they give you is the SSID. So with this information, our devices can connect to the wireless network. Now in a coffee shop or your friend's house, this wireless network might be big enough. For bigger wireless networks, however, we often need to extend our wireless network using multiple access points. When we use multiple access points like this, it's called an extended service set. In an extended service set, each access point will have a unique BSSID to identify the device. The same SSID, however, can be used on multiple access points to extend the range of the wireless network. This allows the user to roam from access point to access point without needing to reconnect. This appears to the user as a single seamless network. Okay, great, so now we have the basics down. Let's talk about how we can actually send data wirelessly through the air. The way our devices can talk to each other without the need for physical cables is by using electromagnetic waves. This works by sending an alternating current into an antenna, which creates magnetic fields that propagate out as waves. If we take a close look at these waves, we can see that they go up and down, up and down, up and down. These are called cycles. Each time a wave returns to its starting point, this is one cycle. It's common to measure these cycles when the wave goes up, down, and back to the start, just as you can see here. We measure wireless frequencies in hertz. A single hertz means one cycle per second. So in this example, we have 4 cycles within 1 second. 1, 2, 3, and 4. This means this example has a frequency of 4 hertz. Now hertz is actually quite a small measurement, so instead we can also use kilohertz, which is 1000 hertz, megahertz, which is 1 million hertz, and gigahertz, which is 1 billion hertz. These electromagnetic frequencies have a lot of different uses. If we look at this table, we can see the radio frequencies measured in hertz, as well as some examples of their uses. Radio frequencies range from 3 kHz to 300 GHz. You have probably heard of radio frequencies before. Things such as radio and TV use radio frequencies. This is also where the wireless networking frequencies are. As we can see from this table, each use is separated by using a different frequency range, which are called bands. Wireless uses 2 main frequency bands, 2.4 and 5 GHz. Now, just to make things a bit more complicated, these bands are then split into separate channels. If we look at the 2.4 GHz band, which is actually 2.400 to 2.4835 GHz, we can see that it's split into different channels. The reason we use channels is to split the wireless bands into smaller, more manageable pieces, allowing us to control things like congestion and interference. The 2.4 GHz band has 14 channels. However, a lot of these overlap, which can cause interference. So instead, it is recommended to use channels 1, 6, and 11 to avoid any problems. This is because these channels do not overlap with each other, minimizing any interference. The 5 GHz band, as we can see here, does not have the issue of overlapping channels. So why do we care about frequencies and channels? Well, you're going to need to choose which band and which channel you will be using. Generally speaking, the choice comes down to 2.4 GHz, which has a longer reach but slower speeds. It also is usually a bit more congested by other devices. 5 GHz has a shorter reach but can use faster speeds. Now, when looking at different channels, this only really matters if you have multiple access points or multiple wireless networks close by. If you only have one, then any channel will work. When there are multiple wireless networks within range, this is when interference can occur. So it's best to choose a separate, non-overlapping channel. Okay, so that was a lot of information. Everything we just looked at is part of the IEEE standard 802.11. Now, as wireless technologies has evolved and improved over time, amendments have been made to the 802.11 standard. Here you can see the amendments and the characteristics for each. You may have seen these before if you've ever purchased a home router. It's important to note that for two devices to talk to each other, they both need to support the same amendments. Luckily, devices can be compatible with multiple amendments, so you shouldn't run into any problems. So before we finish this video, I just want to quickly go over some other wireless modes that our access points can operate in. First, let's look at repeaters. Repeaters do exactly what they say on the tin. They receive a signal from an access point and then repeat that signal in order to extend the wireless coverage. It's not always possible to run additional cables to add another access point. So in these situations, we can use repeaters instead. Next, we have workgroup bridges. Workgroup bridges act as wireless clients to a wireless access point. They can then connect a wired device to that wireless network. So why would you want to do that? Well, for example, say we have a printer or a PC that does not support wireless connections. We can then use a wired connection to that workgroup bridge, which will then in turn connect to the wireless network. Quick note here, there are two types you might encounter. Universal workgroup bridges. This is the 802.11 standard and only allows one wired device to be bridged to a wireless network. Workgroup bridge is Cisco's own version allowing multiple devices to connect. The next mode is outdoor bridges. Outdoor bridges are used to connect two remote networks over a long distance. For example, you may have two office buildings that you want to connect, but it's not possible to lay any cables, maybe because there's a busy road or like a river or something like that in between. In this case, you can use outdoor bridges with specially focused antennas to connect networks over a long distance. It's like running a really long Ethernet cable, but through the air. This is known as a point-to-point outdoor bridge, but you can also have point-to-multi-point outdoor bridges where more than one remote site connects back to the main network. So the last one to talk about is mesh mode. When you have a very large area to provide wireless coverage for, it's not always possible to connect every access point via cables back to the wired network. So instead, we can use mesh mode to daisy chain multiple access points together. The way this works is each access point will have two radios. One will use a channel to backhaul client traffic from the access point back to the wireless network, and the other will use a channel to maintain that basic service set network. This creates a seamless wireless network across large areas. This video is part of the full CCNA course, which you can find in the description below. Okay, so that is it for wireless networks. Frequencies, cycles, and hertz can be intimidating at first, but the concepts are pretty straightforward if you stick with it. If you like this video, don't forget to give it a thumbs up, leave a comment, and subscribe. Support from you guys really helps this channel grow. Other than that, thank you for watching. Hey, what's up guys? Welcome to Cert Bros. In this video, we're going to be talking about access control lists. So what is an access control list? Access control lists, also known as ACLs or simply access lists, are rule-based lists that are used by switches and routers to identify traffic. They can identify traffic based on the source address, destination address, and port numbers. The most common use for an access list is to deny or permit traffic, but there are other uses for access lists such as configuring network address translation and quality of service. Let's take a look at a quick example. This router has an ACL configured. The ACL is configured with rules that tell it which traffic is allowed to pass and which traffic is not. For example, we may want to allow all traffic destined for this server. But at the same time, we may want to block all other traffic to any other host. This is all possible with a very simple access list. Okay, so now we have an idea about what an access list does. Let's see what one looks like. Here is a simple access list. It consists of one or more lines called rules which specify if traffic should be permitted or denied. Don't worry, we'll look at what each bit means in just a moment. The first thing you'll probably notice is the number on the left. This represents the order of each rule. The reason it goes up in tens is to give you the flexibility to come back at a later date and add rules in between the existing ones. Why does that matter? Well, the order of the list is very important. When a router or switch receives some traffic, it checks the access control list. It starts at the top of the list and it works its way down. It keeps going until it finds a matching rule. As soon as a matching rule is found, it stops looking and applies that rule. This means you have to be very careful to put the rules in the right place. Otherwise, you could deny traffic that you're trying to permit or permit traffic that you're trying to deny. We'll see this more as we go. Another very important note here is that if no matching rule is found, the traffic will automatically be denied. There is an invisible deny everything rule at the bottom of every access list. This is known as the implicit deny. Okay, so now we know what an access list does and what it looks like. Now let's take a closer look. There are three types of access list. The first is a standard access list. Now, when you configure an access list, you use a number to identify the type of access list you want to configure. A standard access list uses any number between 1 and 99. Then Cisco decided to expand this to also include 1300 to 1999. This expansion meant we can configure a lot more access lists per device. Standard access lists only use the source address to identify traffic, so this can be quite limiting. The second type of access list is called an extended access list. Extended access lists uses any number between 100 and 199, and expanded numbers between 2000 to 2699. Extended access lists allow us to identify traffic not only on the source address, but the destination address, protocol, and port number as well. So we can have a lot more granular control with extended access lists. The last type I want to mention is called a named access list. A named access list allows standard or extended lists to be given names rather than numbers. If you have multiple access lists on a device, named lists make it easier to identify what each list does, making them easier to manage. We're going to look at all three of these in a bit more detail. First, let's look at standard access lists. This is a command to configure a single standard access list entry. It can look a bit intimidating at first, so we're going to break it down. The first part specifies the access list number. Remember, any number between 1 and 99, or 1300 to 1999, means this will be a standard access list. The next part is the action. Do we want to permit this traffic, or do we want to deny it? We then have our source IP address. And finally, something called a wildcard mask. Now the wildcard mask will need some further explaining. A wildcard mask works with an IP address. It's like an inverted subnet mask. The job of a wildcard mask is to identify the bits of an IP address that needs to match and the bits that don't. To do this, you need to compare the wildcard mask with the IP address. Wherever you see a 0, this means that corresponding bit must match. Wherever you see a 1, this means the bit does not need to match. So in our example here, we have the address 192.168.10.0 and the wildcard mask of 0.0.0.255. This means it will match any traffic with the source address between 192.168.10.0 to 192.168.10.255. Because the wildcard mask states that the last 8 bits don't need to match. So to summarize this rule, it will permit any traffic coming from the source address 192.168.10.something. Okay, so that was nice and simple. Let's now look at an extended access list. This is a command to configure a single extended access list entry. As you can see, there is a bit more to it than the standard access list. Don't worry though, we're going to break it down. The first part specifies the access list number. Because we're now configuring an extended access list, we will use something between 100 and 199, or 2000 to 2699. The next part is the action. So this time we will be denying this traffic. Next we have a new section. This matches the traffic protocol. In this example we have TCP, but this could be UDP, EIGRP, OSPF, etc. Then we have the source IP address, followed by the source wildcard mask. Then we have the destination IP address and the destination wildcard mask. After that we have something called an operator. An operator is used to match port numbers. We have a few different operator options. GT means greater than, LT means less than, NEQ means not equal to, and EQ means equal to. Range means included in the range you specify. In this example, we're going to use EQ, which means equals to, and then we'll specify the port number. We can do this using the port number itself, or we can use a keyword for common ports. Here I typed FTP, meaning port 21. An important note here, when configuring an extended access list, the source IP and port number always comes first. Okay, so to summarize this rule, deny all TCP traffic coming from 192.168.10.something with a destination IP address of 192.168.20.50 and a destination port number of 21. The last one we need to look at is a named access list. Now luckily, named access lists are pretty similar, they're just configured slightly differently. The first thing you need to do is type IP access list. Then you specify if you want to configure a standard or an extended access list. Then you just need to choose a name. Here I've chosen Certbros for the name. Then you enter the access list configuration mode, where you can add the rules in the same way as before. So this access list will deny any TCP traffic with a source IP address of 192.168.10.something, with a destination IP address of 192.168.20.50 and a destination port number of 21, which is FTP. After that, it will permit any IP traffic with a source IP address of 192.168.10.something and a destination IP address of 192.168.20.50. Can you see the importance of having the correct order? If these two entries were the other way around, then FTP traffic would be permitted because the bottom rule would never be checked. So that is how you configure the three types of access list, but you also need to be able to read the lists. Let's take a look at a few examples and try and figure out what they do. Here's our first list. We know it's an extended list because it says extended at the top. But not only that, it also has a number of 101, which hopefully by now we know is an extended access list number. Below this, we have our list rules. The first one states, deny all TCP traffic destined for 192.168.10.something with a destination host address of 192.168.20.50 and the destination port number of 21. Now, access lists that have a 32-bit wildcard mask, or 0.0.0.0, meaning one IP exactly, will show a host address. You can even use the keyword host when configuring it. The next rule is the same, but this time we are blocking telnet traffic. And the bottom one permits any IP traffic from 192.168.10.something with a destination host address of 192.168.20.50. Nice and easy, right? While the next one is even easier. This is a standard list. Of course, it says standard at the top, but it's also using a standard number. Remember, standard access lists only filter based on the source IP address. So this list is permitting traffic from host 192.168.10.10, 15, and .20. Remember, all access lists have an implicit deny at the bottom, so everything else will be denied. Okay, let's look at the last example. This is an extended access list, but this time it doesn't have a number. Instead, it has a name. The first rule permits TCP traffic, and there is a keyword here that we haven't seen yet. We can use the any keyword to specify any IP address. So in this case, any source IP. And then we have the destination host address of 192.168.20.50. And which port do you think www means? HTTP port 80. The second rule is the same, but it's permitting FTP traffic on port 21. Hopefully this has given you a good understanding of access lists, what they're used for, and the different types. This video is part of the full CCNA course, which can be found in the description, so please feel free to go and check that out. If you like this video, don't forget to give it a thumbs up, leave a comment, and subscribe. The support from you guys really helps this channel grow. Other than that, thank you for watching. Hey, what's up guys, welcome to CertBros. In this video we're going to be looking at VLANs. Okay, so VLAN stands for Virtual Local Area Network. Using VLANs, we can virtually separate our LANs into smaller chunks. But why would we want to do that? Well, there are a few reasons why we might want to use VLANs. One of the main reasons is something we've already spoken about, and that is broadcast traffic. So let's remind ourselves about broadcasts. A LAN is a single area of a network. And in this case, we have a single broadcast domain created by our switch. If host A sends a broadcast, then every device will receive it. That's fine for our 4-computer network, but let's imagine each computer represents an entire department. Very quickly, broadcast traffic can start to slow down our networks and devices. So we need a way to manage all of this traffic. One way is to add a router. This would create separate broadcast domains per interface. But it's an extra bit of hardware to purchase, install, cable, and manage. Another, more radical option is to physically split the network into separate sections. This would create broadcast domains for each department. Traffic wouldn't be sent from one department to the other, which drastically reduces our broadcast overhead. But this option still has the issue of needing to purchase and set up new equipment, and neither one of these options is very scalable. Say we wanted to add a new department, both options would require work to set up. And we don't want to do that. This is where VLANs come in. VLANs give us all of the benefits of physically separating our network, but with the added bonus of being able to do this virtually. The traffic still behaves in the same way as if it was physically split. Traffic isn't forwarded to any other departments. And it's almost like having 4 miniature switches inside our single one. The way this works is by assigning interfaces to specific VLANs. Only interfaces in the same VLAN can communicate with each other. In this example, finance is yellow, IT is red, sales is green, and HR is purple. I'm using colors, but in reality, you will probably use numbers such as VLAN 10, VLAN 20, etc. If we wanted to add a new finance server, then we just need to assign that interface to the finance VLAN, and communication between those two interfaces is allowed because they're on the same VLAN. If we wanted to add a brand new marketing department, then we just create that VLAN and assign it to an interface. As you can see, VLANs make it very, very easy to control broadcast domains. It's also scalable. We don't need new equipment or to recable everything anytime we want to make a change. Okay, so that's the overview. Let's look at how this works in a bit more detail. Straight out of the box, Cisco and most other switches have a default VLAN called VLAN 1. Every interface is assigned the default VLAN. So this means every interface can talk to each other. From here, we can start to make our own VLANs and split up our switch. We may want to make a VLAN called VLAN 10 and another called VLAN 20. You can add up to 4094 VLANs. This is the maximum number that is supported. So now interfaces assigned to VLAN 10 can only communicate with other interfaces assigned to VLAN 10. And it's the same for VLAN 20. VLANs aren't restricted to just one switch. We can have the same VLANs across multiple switches. This makes it very versatile and scalable. But this does leave us with a problem. If interfaces can only communicate with other interfaces in the same VLAN, which VLAN do we assign to the link between our two switches? If we leave it as the default VLAN, VLAN 10 and VLAN 20 won't be able to send traffic. If we assign it to one of our new VLANs, then only that VLAN can send traffic between the two switches. The solution is a special type of interface called a trunk. So there are two types of ports on a switch, an access port and a trunk port. When a port is assigned to a VLAN, like VLAN 10 and VLAN 20 here, this is known as an access port. An access port is designed for endpoint devices to access the network, such as computers and laptops. Now a trunk port can send traffic from different VLANs. They're used to send traffic between networking devices. This leaves us with another problem though. How does the receiving switch know which VLAN the traffic belongs to? The whole point of a VLAN is to separate traffic. So when a trunk sends data, that could be from VLAN 1, VLAN 10, or VLAN 20, it needs a way to identify which VLAN that traffic belongs to. This is done by using something called a tag. To understand tags, we need to take a couple of steps back. Now, most devices, including computers, do not know what VLANs are. Some devices are VLAN aware, such as IP phones, but most are not. So a computer generates a frame as normal. When that frame arrives at a switch, it's the switch that handles the VLANs, then is forwarded to the correct destination. The sending computer and the receiving computer have no idea that VLANs were used. Now, when we have multiple switches connected with a trunk port, there is an extra step. The computer sends the frame as usual, but when the switch sends the frame over the trunk port, it adds a new bit of information. This is called an 802.1q tag. 802.1q is the IEEE standard. It can also be called .1q. This tag is 4 bytes and it contains a few bits of information. TPID, or Tag Protocol Identifier. This is used to identify the frame as an 802.1q tagged frame. It could also be ISL, but is rarely used today. TCI, or Tag Control Information. This contains 3 bits of information: the priority, DEI, or Drop Eligible Indicator, and most importantly, the VLAN ID. This tag field is then read and removed by the receiving switch. So to recap, the frame is untagged when it's sent from the computer. It's tagged over the trunk port. It's then sent to the destination computer untagged. And our computers are again none the wiser. The next thing we need to talk about is something called native VLANs. A native VLAN is configured per trunk interface. It's the VLAN that the switch assumes the frame is on if it arrives on a trunk port with no tag. By default, the native VLAN is VLAN 1. So let's say both of our computers are assigned to the default VLAN 1. Just like before, the frame is sent untagged to the switch. Now, if a switch is sending a frame across a trunk port that belongs to its native VLAN, the frame is not tagged. When a switch receives a frame on its trunk port without a tag, it will assume that frame belongs to its native VLAN, which in this case is VLAN 1. It will then forward that frame to the destination, again untagged. So you might be wondering why we use native VLANs. And there are a few reasons why. Hubs can't read or write tags. All hubs can do is forward frames. Let's say we have a hub in the middle connected to another host. Using untagged native VLANs means we can send frames to our new host. If we didn't use native VLANs and the frame was sent tagged, then the host will just discard the frame because it doesn't understand VLAN tags. So, a native VLAN is configured per trunk interface. This can lead to problems. For example, let's say we change one side of our trunk to have the native VLAN of 20 instead of 1. We now have 2 switches with different native VLANs. Our computer will send the frame as before. The first switch will see the interface is assigned to its native VLAN and then forward that frame untagged across the trunk. Do you see the problem here? The second switch will assume the traffic should belong to its native VLAN, VLAN 20, and the frame will not be sent to the destination computer on VLAN 1. Luckily, in real life, you will be alerted to this type of configuration on the switch. You'll probably see a message like this, saying native VLAN mismatch. This video is part of our full CCNA course, which can be found in the description, so please feel free to go and check that out. Don't forget to like, comment, and subscribe. The support from you guys really helps this channel grow. Other than that, thank you for watching. Hey, what's up guys? Welcome to Certbros. In this video, we're going to be talking about ARP. So, what is ARP? ARP stands for Address Resolution Protocol, and is designed to discover MAC addresses and then map them to an IP address. So let's see how this works. In our example, we have 4 computers and a switch. Our computers have been assigned IP addresses 192.168.0.1, .2, .3, and .4. Let's say host A wants to communicate with host D. We already know the IP address. Maybe we typed it in manually. But remember, switches are layer 2 devices, which use MAC addresses, not IP addresses. So for host A to communicate with host D, it somehow needs to find out its MAC address. The way it does this is simple. Host A will shout out to the entire network saying, "Who is 192.168.0.4? Tell me your MAC address." And that message is sent as a broadcast. We've already looked at broadcast messages, and remember, they will be sent with a destination address of all Fs. And the switch will send this out of every interface except the one that received it. Host B and host C will look at this message and think, 192.168.0.4? That's not me. And they discard the frame. But when host D sees the message, he says, "Ooh, 192.168.0.4, that's me. Here is my MAC address." And then host D replies with his MAC address directly to host A. When our computers learn MAC addresses, they are stored in a table for future use. It lists the known IP addresses and their associated MAC addresses. This table is called the ARP cache. From this point forward, if host A needs to talk to host D, it just needs to look up the IP address in the ARP cache to find the correct MAC address. And now they can both send frames happily. So that was pretty simple. Let's see this live and in action. I'm going to click the Start button and type PowerShell. Now we're going to need to run this as admin, so right-click, Run as Administrator. Accept the UAC, and when that loads, I'm going to start by typing ARP-A. This is going to show us the computer's ARP cache. We have the internet address, which is the IP address, the physical address, which is the linked MAC address, and we have the type. This shows us if the MAC address was learnt by ARP or if it's a static entry. You can see we have 3 static entries, and this is by default. The top one is something called a direct broadcast address. You should be able to recognize this by the IP address. It's the last IP in the network. You should also be able to recognize it by the associated MAC address, which is all Fs. This tells us this is a broadcast address. The bottom 2 are multicast addresses. You can see that from the first 6 characters of the MAC address. So, because my computer already knows the MAC address of 192.168.0.4, I'm going to run ARP-D 192.168.0.4, and this is going to delete that entry. If I then type ARP-A again, we see that entry has been removed. Now I'm going to open up a program called Wireshark, which will capture all of the traffic on this computer. We just need to select the interface and hit the Start Capture button. While that's running, I'm going to open PowerShell again and type ping 192.168.0.4. And this will trigger an ARP request. Once the ping is finished, we'll head back over to Wireshark and hit the Stop button. There's not a huge amount to go through here, but if you're trying this at home, you will likely see a lot more information. This is a fresh PC, so not many applications are running. We can filter the capture by clicking at the top and typing ARP. Now we can see our ARP conversation happening. We can see the source and destination. Keep in mind though, Wireshark will try to resolve these MAC addresses to something a bit more readable. If we look at the info column, here we can see ARP requesting the MAC address of 192.168.0.4. With the first request selected, we can look at the bottom of the screen and see our source and destination MAC address. So host A is the source and the destination is a broadcast MAC address. If we select the second one down, which is the reply, you can see in the info column, host D is replying with its MAC address. This reply is saying, "Hey, that's me. This is my MAC address." If we look at the bottom, we can see host D's MAC address is now the source, and host A's MAC address is now the destination. And now if we go back to our PowerShell window, run ARP-A again, we can see that the entry is now back in the table. Let's look at one more scenario. Here we have two hosts, a router and a web server. If host A wants to communicate with the web server, what will it do first? Well, if we type in the IP address of the web server, host A will compare that IP address with its own. It will look at 192.168.0.1 and 10.10.10.10, and it will realize the web server is not in the same network. ARP requests only happen in layer 2 networks. So we can't send an ARP request to the web server. So what do we do? Knowing it needs to get off the network, host A will do the same ARP request, but not to the web server, through its default gateway, which in this example is the router. The default gateway is like the door out of the network and is configured alongside the IP address. If a device needs to communicate out of the network, it's sent to the default gateway. So we send an ARP request to 192.168.0.254 and request the MAC address. Host B will drop this request. The router will respond with its MAC address just like we've seen already. And now we have the MAC address for the default gateway, host A can start to send data. The data will contain the MAC address of the router, but it will have the IP address of the web server. The router will handle things from there. We will go over this in more detail as we move on to routing. This video is part of our full CCNA course, which can be found in the description, so please feel free to go and check that out. That's it for ARP. If you liked this video, please give it a like, comment, and don't forget to subscribe. The support from you guys really does help this channel grow. Other than that, thank you for watching. Hey, what's up guys? Welcome to Certbros. In this video, we're going to be looking at IP addresses. More specifically, IP version 6 addresses. So, we've already looked at IP version 4 addresses in the previous videos. But there's a problem. When IP version 4 first came out, the people that designed it sat back in their chairs and said, "We've done it. We've created every IP address that anyone will ever need." How many addresses did they create? 294,967,296 addresses. Which sounds like a lot, right? But at the time, they couldn't have imagined the massive explosion of devices that would require an IP address. If you think about every device you own, like a PC, laptop, smartphone, TV, etc., it quickly became apparent that we would soon run out of IP version 4 addresses. The solution is to eventually move over to the new IP version 6. IP version 6 provides us with, well, I'm not even going to try and say that number, but it's a lot. Aside from the number of addresses, IP version 6 also brings a lot of other improvements that makes it a lot more efficient and practical. Okay, so let's dive into what an IP version 6 address looks like. Let's first remind ourselves of IP version 4. It's 32 bits in length. Remember, bits refer to the binary digits of the address. It contains 4 sections called octets, which are separated by dots. And, in theory, each octet can contain any number between 0 and 255. Now we're familiar with our good old friend IP version 4, let's bring in an IP version 6 address. Now, at first, this address looks pretty scary. But don't worry, we're going to break it down step by step. First, let's do some comparisons. We know our IP version 4 address is 32 bits long, but our IP version 6 address is 128 bits long. This is where we get our massive IP address space from. IP version 4 has 4 sections called octets. IP version 6 has 8 sections, but these are commonly called hextets. IP version 4 uses dots to separate octets, but IP version 6 uses colons to separate hextets. So let's get rid of our IPv4 address and go into some more detail. The first thing you probably noticed is there are letters in this IP address. IP version 6 is hexadecimal, meaning each character can be between 0 and 9, or A and F. Let's take a look at how IP version 6 works when it comes to binary. This is especially important when it comes to subnetting. Each hexadecimal character is made up of 4 binary bits. These bits can either be a 0 or a 1. Each bit represents a value of 1, 2, 4, or 8. It doubles with each column from right to left. Wherever we see a 1, that toggles that column on. And wherever we see a 0, that toggles the column off. We then add up all of the columns that have a 1, and this gives us our number, or letter. So let's take the first number from the address, which is 2. How do you think we can make the number 2 from our binary bits? We simply add a 1 in the 2 column. All other columns stay as 0 because we don't need them. So the binary value for our first number is 0010. We're going to go through a few of these just to make sure it sticks. The second number in our address is 0. How do we get 0? Well, we simply leave all the columns off. So this gives us a binary value of 0000. Our next number is also 0, so it's the same. Now we have number 1. Just like with before, we turn on the column for 1 and we leave the rest as 0. Our binary value is 0001. We have yet another 0, so we know our binary value will be, well, all zeros. This next one we do need to look at. How do you think we get the letter D from our binary chart? Well, if you remember, I mentioned that each character can either be 0 to 9 or A to F. Clearly, we can make bigger numbers with our binary chart than 9. In fact, we can get up to the number 15 if we turn on all the columns with a 1. The problem is, we can't use double digits. So instead, we swap out 10, 11, 12, 13, 14, and 15 for A, B, C, D, E, and F. So now we know that, how do we get the letter D? D has replaced the value 13. So this is the number we need to get. You should always start with the highest number you can. And in this case, that number is 8. Then the second highest, which is 4, this gives us 12. So we only need one more. We'll leave the 2 column off because this would make our number too high, and turn on the 1 column. Add this all up and we get 13. So that means our binary value for D is 1101. Hopefully you get the idea by now. If you were to continue doing this, you would eventually end up with the full binary value. Okay, so that's our brief binary lesson. It's not something you'll do every day, but it is important to understand, especially when looking at some more in-depth subnetting. Okay, so just like IP version 4, IP version 6 has a network section and a host section. The way IPv4 does this is by using a subnet mask. However, IP version 6 has gotten rid of the subnet mask, and instead it just uses a / and the number of network bits, which you should be familiar with from IP version 4. So, in our example, /64 is half of our 128-bit address. /64 addresses are common when it comes to IP version 6. It splits it nicely down the middle and ensures we have plenty of networks and plenty of hosts. But be prepared to see different numbers. Remember, each character is 4 bits long and each hextet is 16 bits. We'll now look at how we compress this address to make it look a little nicer. I'm sure we can all agree that this is a lengthy address, and the thought of typing this out over and over again is simply horrific. But there are a couple of tricks that we can do to make this address a bit more bearable. The first trick is to remove continuous zeros. Because we find ourselves with so many addresses, a lot of the time we see multiple hextets next to each other that contain only zeros. We can simply replace all of these zeros with a double colon. When the computer sees this address, it sees the double colon, works out there are 2 missing hextets, and then fills in the zeros. The rule to this trick is it can only appear once. For example, if we change this address slightly and add another hextet of zeros, we cannot add another double colon. If a computer looked at this address, it has no way of filling in the missing pieces. How would it know if the address is missing 8 zeros from here and 4 zeros from there, or 4 zeros from here and 8 zeros from there? So this is why it can only happen once. But there is another trick we can use. We take all of the leading zeros from each hextet, so where it starts with 1 or more zeros. We have 1 here and 3 there. Then we simply remove them. So now, when the computer looks at DB8, it realizes there is a missing character and it fills in the gap. The same thing happens on this hextet. Note that even though it's all zeros, because we already used the double colon, we need to leave the last 0. And this is the address we're left with. Still pretty large, but it's a big improvement from where we started. Okay, so moving on. Just like IP version 4, there are different types of IP version 6 addresses, and they serve different purposes. What we see here is called a global unicast address. You can think of this like a public IP version 4 address that is routable over the internet. Unlike IP version 4, because we have such a massive amount of IP addresses, we no longer need to rely on private addresses. Every device can have its own public IP address. The first part of this address is known as a global prefix. This is what your ISP will provide you as a block of IP addresses. This global prefix will be a minimum of 48 bits long. Once we have the global prefix, we can then use the next 16 bits for our subnet ID. 16 bits gives us over 65,000 subnets to play with, and that leaves us nicely with a 64-bit host or interface ID. Okay, so let's look at some other address types. We have global unicast, which we just looked at. This is a publicly routable address like the IP version 4 public IPs. The prefix to identify these addresses is 2000:3. This means the first 3 bits identify a global unicast address. It will start with either a 2 or a 3. Next, we have a unique local address. This address is like an IP version 4 private address. These are not globally routable. The prefix to identify a unique local address is FC00:7. Using the first 7 bits, a unique local address will always start with an F followed by either a C or a D. Link local addresses. Think of these as quick, automatic private IP addresses that are not routable over a network. They are designed to communicate only within a single area of a network. You may have seen the dreaded 169.254.something.something address when your computer can't connect. This is pretty much the IP version 6 replacement. You can identify a link local address because it has a prefix of FE80::/10. This means the link local address will always start with FE. Multicast addresses. These are addresses that are sent to a group of computers or devices listening for that particular multicast address. IP version 4 used to also use broadcast addresses. These were sent to all computers within a network. These have now been scrapped with IP version 6. Multicast addresses are easy to spot because they always start with FF. Okay, last but not least, we have something called an Anycast address. Now these are interesting because IP version 6 allows us to assign the same IP address to multiple devices. The data is then sent to the closest device with that address. There isn't a specific IP range for Anycast addresses. They use the same range as global unicast. So as you can see, the prefix is the same. Now it's really important to be able to look at an IP version 6 address and identify the type. So to recap, global unicast addresses will start with either a 2 or a 3. Unique local will start with an F followed by C or D. Link local will always start with FE. And multicast will always start with FF. Okay, so I think that's enough for one video. You should now understand the fundamentals of IP version 6. This video is part of our full CCNA course, which can be found in the description, so please feel free to go and check that out. If you liked this video, don't forget to give it a thumbs up, leave a comment and subscribe. The support from you guys really does help this channel grow. Other than that, I hope this video helped and thank you for watching. Hey, what's up guys? Welcome to Cert Bros. In this video, we're going to be looking at binary. Okay, so in the last video, we looked at IP addresses, what they are and what they do. In this video, we're going to take it up a notch. Binary is how computers process data. And it's just a whole bunch of ones and zeros. You've likely seen or heard about binary, especially in those cheesy hacker or cybersecurity videos. It can look intimidating at first, but it's actually very simple. An IP version 4 address is 32 bits long. This means the address is made up of 32 binary digits. Each digit is called a bit. The IP address contains 4 octets. Each octet contains 8 binary bits. When we type in an IP address, the computer will convert that into binary. And to fully understand how IP addresses work, we need to be able to do the same. We're going to use just 1 octet for our conversion, and then the same process is repeated for the rest of the IP address. So here we have 8 binary bits. These bits can either be a 1 or a 0. So how do we make numbers like 192 from 1s and 0s? Well, each bit represents a value. The value doubles in size from right to left. This is called the power of 2. Using this chart, we can see each bit is assigned its own column. It's important to know that 1 means on and 0 means off. This means we can turn columns on or off just by adding either a 1 or a 0. So let's try it. All of our columns currently have a 0. which means they're all off. What value does 8 zeros give us? Well, because all columns are off, there's nothing to add up, so our binary value is 0. If we turn on the 1 column by adding a 1, what value does that give us? It gives us 1. If we put a 1 in the 2 column, that gives us a value of 2. Pretty straightforward so far, right? Okay, this time, let's turn on the 1 and the 2 column. What do we do here? We need to add up all of the columns that have a 1. So our value here would be 3. Hopefully that makes sense. Let's try one that's a bit more difficult. Our binary value is 00101101. Again, we just need to add up all of our columns. 32 plus 8 equals 40, plus 4, so that's 44, plus 1 equals 45. So 45 is our number. Okay, so now we've gone over the basics, let's bring in an IP address and convert it to binary. Remember, there are 8 bits in each octet, so we're going to do this one at a time. The first number in our IP address is 192. So this is the number we need to generate from our binary bits. We always start with the highest value we can. In this case, 128, so we put a 1 in that column. That leaves us with 64 remaining, and that just so happens to be the next column, so we'll add a 1 there as well. This means our binary value for 192 is 11000000. The next number in our IP address is 54. Again, we start with the highest number possible. This time, that's 32. That leaves us with 22. So we can add 16, then we're left with 6. We can get that by adding the 4 and then the 2. And that's it. So the binary value for 54 is 00110110. The next number is 103. If you think you're getting the idea by now, try pausing the video, writing out this power of 2 chart, and trying to work out how to get 103. It's okay, we'll wait. Okay, that's long enough. We start with 64 because that's the highest value we can use. Add 32, that gives us 96, so only 7 left to go. We'll add 4, 2, and 1. Meaning the answer is 01100111. And the last one to do is 29. So we need 16, 8, 4, and 1. Meaning our last binary value is 00011101. And we have now converted our IP address into binary. Don't worry though, this isn't something you'll need to do all of the time. But it is extremely important that you understand how this works, especially as we progress. If you're not great with maths, again, don't worry. The more you practice this, you will start to memorize it. Without thinking, you'll know that 128 plus 64 equals 192. Okay, so moving on. In the last video, we spoke about how an IP address is split into a network section and a host section. The way we know which is which is with a subnet mask. Our IP is a class C address, so we should know that the default subnet mask is 255.255.255.0. Previously, I said wherever there's a 255, this is the network section, and wherever there is a 0, this is the host section. And that's true in the simplest form. However, it can get a bit more complicated than that. The real way to see which part of an IP address is the network section is by looking at the subnet mask binary bits. Anytime you see a 1, this bit is the network section. Anytime you see a 0, this is the host section. I know it may seem overkill with this example, but as we move on into subnetting, it's extremely important you understand how this works. Now, instead of a full subnet mask, you will often see it written as a / and then the number of network bits. In this case, instead of 255.255.255.0, we could write it as /24. This is usually added to the end of the IP address. Let's take a closer look at the host section. You can see we have 8 bits. Thinking back to our chart, how many host addresses can we have with 8 bits? We can have all zeros, all ones, or anything in between. 255 is the number we get if we add up all of the columns. This means we have a total number of 256 possible combinations, and that's including 0. There is a catch though. You cannot use the first or last IP address for a host. These are reserved. The first address, in this case 192.54.103.0, is the network address. And the last address, 192.54.103.255, is a broadcast address. This is used to send messages to all computers in this network. So we only have 254 usable hosts. So just remember, you cannot assign the first or the last address to a host. Okay, so that's the basics of binary. We'll be using this a lot as we go, especially when we move on to subnetting. This video is part of our full CCNA course, which can be found in the description. So please feel free to go and check it out. If you like this video, don't forget to give it a thumbs up, comment, and subscribe. The support from you guys really does help the channel grow. Other than that, I hope this video helped, and thank you for watching. Hey, what's up guys? Welcome to Cert Bros. In this video, we're going to be looking at IP addresses. So we're going down the TCP-IP model as if we were sending data, so top to bottom. In the last videos, we saw how data can be sent using TCP and UDP. We also saw how data gets to a particular application using port numbers. Now we're moving down to the network layer to see how that data actually gets to the destination. This layer is responsible for IP addresses. So, what is an IP address? An IP address is a unique identifier assigned to each device connected to a computer network. The most common analogy for an IP address is the postal service. For the postal service to work, every house needs to have its own unique address. And if you need to send a letter, not that anyone sends letters anymore, but you need to write the destination address on the envelope. That way, when you send the letter, the postman knows exactly where to deliver it. Now, the address must be unique. Otherwise, your post could end up going to somebody else, or you could start receiving somebody else's post. And that can sometimes not go so well. Computers work in the same way. Each computer in a network needs to have a unique address, called an IP address. And when sending data to a computer, just like letters, we need to add the destination address. We also need to include a return address, so they know where to reply. So, let's look at an IP address. This is an IPv4 address, which, at the time of making this video, and probably for a long time after, is the most common. Although we are slowly moving over to the new IP version 6, that will be covered in another video. So, an IPv4 address is 32 bits in length, which means it contains 32 binary digits. We'll look at this more when we go over subnetting. It contains 4 sections, which are called octets. These octets are separated by dots or periods. Each octet, in theory, can contain any number between 0 and 255. Why 255? Well, our 32-bit number is separated into 4 lots of 8, and 255 is the largest number that can be made from 8 bits. Now the address itself is separated into 2 parts. The first part represents the network, and the second part represents the host. To know which part of the IP address represents the network, we used to rely on the first few binary bits. But since the early 90s, we have something called a subnet mask. A subnet mask is always paired with an IP address, and is used to identify the network section and the host section of the address. In its simplest form, whenever you see 255, this is the network part of the address. Whenever you see a 0, this is the host part of the address. It can get a bit more complicated than that, but we'll look at that later on down the line. When learning about networks and hosts and what they mean, it's good to think of it like your address. You share the same street name as your neighbors, but it's the house number that makes your address unique. On the other hand, you can also have multiple streets with the same house number, and it's the same with computer networks. Instead of street addresses, you have network numbers, and instead of house numbers, you have host numbers. Here we have 2 networks, 192.168.5.0 and 192.168.10.0, both with a subnet of 255.255.255.0. When talking about networks as a whole, you often just use 0 for the host section. Inside our networks, we have our hosts, .1, .2, and .3. It's common in a network diagram to just show the host section of the address if you already know the network section. In fact, these IP addresses would be 192.168.5.1, 192.168.5.2, and so on and so on. So with all of that in mind, if we had some data to send to 192.168.5.3 with a subnet mask of 255.255.255.0, where would we send it? Well, if we look at the subnet mask, we can see that the network is 192.168.5. So we know that 3 is our host number. So we send it over to the host in the network on the left. Hopefully that all makes sense so far. Back in the early days of IP, it was decided to split all of the available addresses into groups, and these groups were called classes. The idea was to make address allocation scalable. The main ones being Class A, Class B, and Class C. There is also Class D for something called multicast addresses, and Class E, which is reserved for experimental use. We're going to focus on the first 3. Each class has a range of IP addresses. Class A addresses are between 1.0.0.0 to 126.255.255.255, with a subnet mask of 255.0.0.0. Class B addresses are between 128.0.0.0 to 191.255.255.255, with a subnet mask of 255.255.0.0. And Class C addresses are between 192.0.0.0 to 223.255.255.255, with a subnet mask of 255.255.255.0. Whew. After that, never want to say 255 again. So this was all to control the number of hosts available on each network. Class A has 3 octets available for host allocation. This means we can have 16,777,214 hosts for a single Class A network. Massive, massive networks. Class B has 2 available octets for host allocation. So we can only have 65,534 hosts to a single Class B network. Still a very, very big number. Class C only has 1 available octet for host allocation. So this means we can get 254 hosts per single Class C network. So you need to be able to look at an IP address and know which class it belongs to. The easiest way to do this is to memorize the first octets. If an IP starts with the number 10, straight away you know it's a Class A network. If it starts with 192, you know it's Class C, and so on and so on. But there's a problem. The problem is no one could have predicted the massive explosion of computers and the internet. In fact, there are no more unallocated IP version 4 addresses left. This is why the new IP version 6 has been designed. It will give us more than enough IP addresses for absolutely everyone. But fear not, there is a solution to help prolong the life of IP version 4. The solution is to carve out small sections from all three classes and call them private IP addresses. All other addresses are known as public addresses. They still use the same subnet mask for that class, and they can still have the same number of hosts. The difference is, where public IP addresses need to be unique, private addresses can be used over and over and over again, thus saving millions or billions of public IP addresses. This is how it works. Let's say this is your house. You have a PC, a phone, and a printer. You can choose any private IP range that you want to use. In this case, we will choose Class C 192.168.1.0, and we'll assign our IP addresses. Remember, this is a Class C network, and the default subnet mask is 255.255.255.0, meaning 192.168.1 is our network address, and the last number is our host address. So all of our devices can talk to each other without any problems at all. The beauty of private IP addresses is that they can be used by anyone. For example, your neighbors might also be using the same IP addresses as you are, and that's fine. Private IP addresses only need to be unique within your own network. There is a catch though. Private IP addresses cannot be used over the internet. Otherwise, we would have duplicate IP addresses everywhere, and data would never end up getting to the correct places. For that reason, only public IP addresses can be used over the internet. These must be unique. When you sign up with your internet service provider, they will issue you with a public IP address that you can use over the internet. Usually, they give you just one address, not a block of 65,000 or 254, one. This helps prolong the life of IPv4 because instead of using an IP address for every one of our 6 devices, we are only using 2 public addresses. The way our devices will communicate to the internet through the public IP is by using something called network address translation, which again we will cover in a separate video. Before we finish this video, I will show you how to check your own IP addresses at home. On Windows, you simply open a command prompt or PowerShell. Type ipconfig to see your interface settings. Find your interface. You might have more than one if you have wireless, and you'll be able to see your IP address and subnet mask. For Linux or Apple computers, open a terminal and type ifconfig, and you should see the same information. To view your public IP address, simply open a browser, go to Google, and type in "What is my IP?" and it will show you your public IP address. So we still have a lot to go over when we're talking about IP addresses. We need to cover binary and subnetting, but I think that's enough for one video. This video is part of our full CCNA course, which can be found in the description. So please feel free to go and check that out. If you liked this video, don't forget to give us a thumbs up, leave a comment, and subscribe. The support from you guys really does help the channel grow. Other than that, I hope this helped and thank you for watching. Hey, what's up guys? Welcome to Cert Bros. In this video, we're going to be talking about TCP versus UDP. So let's look back through our TCP-IP model, which should hopefully look familiar to you by now. When sending data, we start at the top of the model and work our way down. We're going to ignore the application layer as it's largely out of our control and start at the transport layer. The two primary protocols at this layer are TCP and UDP. A network application has to choose how to send its data. That choice comes down to, do I want to send it reliably or do I want to send it unreliably? Both reliable and unreliable have their benefits and drawbacks. First, let's look at TCP, or Transmission Control Protocol. The first thing to understand is when we send data, this file for example, is not sent all as one piece. It's sent in lots of different pieces of data. The receiving computer then collects these pieces, puts them all together, and then spits out the file. And that's fine, but what happens if some of the data we send gets lost along the way? The receiving computer won't be able to put the pieces together, and you'll probably end up with a corrupted file. So this is the reason we need some method to reliably send data, something that can resend and resolve missing or corrupted data. And this is exactly what TCP does. TCP is the most widely chosen option for transmitting data. This is because it can reliably send and receive data. If there is a network blip and some of the segments are lost along the way, TCP can recover them, meaning the user experience shouldn't be compromised with half-loaded websites or corrupted documents. The way TCP can provide such a stable and reliable connection is in three ways. First, it uses acknowledgement numbers. Second, it uses sequence numbers. Third, TCP adds a checksum. But before any of that can happen, first we need to start a reliable connection. TCP does this by using what's called a three-way handshake, and it looks something like this. First, the sending computer sends a message called a SYN, which is short for synchronize. The receiving computer then replies with an ACK message. This is short for acknowledgement. And it also includes a SYN message of its own. So this message is called a SYN-ACK. Lastly, the sending computer acknowledges with an ACK message. Now we have an open TCP connection. A similar process is also followed when closing this connection down. Okay, so the next step is to look at sequence numbers. TCP will assign numbers to segments as they are sent. This way, the receiving device can collect these segments, reorder them correctly, and determine if any segments are missing. The sequence number is just one field in the TCP header. These messages are then acknowledged. It's almost like saying, sending data, and the receiving computer says, got it. Sending data, got it. And so on and so on. The way this works is by using sequence numbers and acknowledgement numbers. So I also mentioned a checksum. The checksum is the result of a simple calculation ran against the data. If the data has been transmitted successfully, the checksum ran on the receiving side should match the checksum ran on the sender's side. If there has been some problems along the way and some bits got messed up, then there will be a checksum mismatch and the segment will be discarded. As we've already seen, a TCP header is added to the application data to create a segment. This is what a TCP header looks like. We have port numbers, which we will cover in another video, the sequence and acknowledgement numbers, and the checksum. For now, there's no need to worry about the other bits of information. Now, unreliable communication comes in the form of UDP, or User Datagram Protocol. UDP has none of the error handling, sequencing, or reliability of TCP. You can think of UDP as a kind of machine gun of data, just firing and firing, not caring if data is lost or not. It has one goal, and that goal is to send data. So why would we ever consider using UDP if it's so unreliable? Well, while TCP offers a great connection and reliability, it all comes at a price of resource and latency. This is great for the most common tasks, such as web browsing, file transfers, etc., where we don't mind the latency issue in return for a stable connection. Where UDP is useful is in situations where we need live, real-time connections. For example, voice calls, video calls, and gaming all need fast, real-time connections. We can't afford latencies in these situations. We can handle a loss of voice data because who really cares about a bit of jitter in a voice call? On the other hand, if we start trying to resend voice data, then this could cause a latency and make the call inaudible. So now let's look at a UDP header. As you can see, there is a lot less information here than there is on the TCP header. We only have the port numbers, the length of the data, and a checksum. The small header means less information, but it's lighter and is quicker. Perfect for real-time traffic. That's it for TCP and UDP, two ways to send data for two different purposes. This video is part of our full CCNA course, which can be found in the description, so please feel free to go and check that out. If you liked this video, don't forget to give it a thumbs up, comment, and subscribe. Other than that, I hope this video helped, and thank you for watching. Hey, what's up guys, welcome to Cert Bros. In this video, we're going to be talking about the TCP-IP model. Quick warning, we're going to be referencing the OSI model a lot here. So if you haven't already watched that video, check that out first, then come back. Okay, so what is the TCP-IP model? It's a model to standardize computer networking. Sound familiar? It should, because it's the same description as the OSI model. Now, the OSI model, while widely referenced, isn't used in the real world. The TCP-IP model, however, is the real deal. Thankfully, it's not that different. Here is the TCP-IP model. 4 simple layers: application, transport, internet, and link. And just like the OSI model, it's numbered from the bottom up, but the direction depends on if you're sending or receiving traffic. So this is the original model, but it has been updated. Here is the brand new, freshly designed model. 1 extra layer and 1 renamed layer. That's it. The link layer has been split into data link and physical, and the internet layer has been renamed the network layer. Simple, right? It gets even better when we compare the TCP/IP model to the OSI model. Now, if you remember, the OSI model has 7 layers compared to our 5 here. But when you look at it, you'll notice the application, presentation, and session layers are just shown as application layer in the TCP/IP model. All the other layers line up nicely, which is great because we should already know the concept of how this works. So let's remind ourselves about the protocols and devices at each layer. At the application layer, we have application protocols such as HTTP, FTP, and SMTP. The 2 most common transport protocols are TCP and UDP. Port numbers are also added here. At the network layer, we have the Internet Protocol, or IP. Routers also operate at this layer. The data link layer contains Ethernet. Switches typically operate at this layer, although you can get layer 3 switches that have some routing capabilities. Finally, we have the physical layer. Think of everything we can touch and feel here. Things like cables and network interface cards. Okay, so as we send data, each layer will add its own bit of information. This process is called encapsulation. When we hit the physical layer, the data is transmitted over to the receiving device. The receiving device then starts to decapsulate the data. We saw this in the OSI model, but in this video we're going to take a closer look. We start with our application data at layer 5. This is then passed down to the next layer where the transport information is added. Let's say it's a TCP header. Each time a header is added, this will contain specific information. For example, a TCP header will contain things like the source and destination port number, sequence numbers, and a few more bits of information. We'll go over this in more detail in a separate video. We then move to the network layer, where we add the IP header. This will contain the source and destination IP address, as well as some other bits of information. Lastly, we have the data link layer. Here we add not only a header, but a trailer as well. The header contains mainly the destination and source MAC address, and the trailer contains some error checking information that the receiving side can check and make sure the data has been received correctly. Once the data hits the physical layer, it is physically transmitted. So, we've gone through the encapsulation process. It's important to note that at each stage, the data has a specific name. At layer 5, the data is called, well, it's just called data at this stage. Once the transport information has been added, it's now called a segment. Adding the network layer information makes our segment a packet. And finally, once we add our data link information, the packet becomes a frame. Now, once data has been transmitted, the receiving computer decapsulates the information. It will check the destination MAC address for that frame, and if the frame is destined for our computer, it's processed further. The computer then checks the IP information off the packet. Again, if the packet is destined for our computer, it's processed further. The transport information is read and the application data is sent to the receiving application. So that's it for the TCP-IP model. After looking at the OSI model, thankfully there isn't much else to learn. This video is part of our full CCNA course, which can be found in the description. If you liked this video, don't forget to like, comment, and subscribe. The feedback from you guys really does help the channel. Thank you for watching. Hey, what's up guys? Welcome to Cerberus. In this video, we're going to be looking into the world of cloud computing. We're going to be looking at what it is, how it works, and how you can get started for absolutely free. If you're new here, this channel uploads regular IT training videos just like this one. So if you like what you see here today, don't forget to smash that like button and consider subscribing so you don't miss out on any new videos. Before we get started, I want to say a big thank you to Linode for sponsoring this video. Linode is the largest independent cloud provider, and they make cloud computing really, really simple. We'll talk more about these guys later and how you can get started with cloud computing absolutely free. Okay, so before we start to understand cloud computing, we need to understand on-premise computing. On-premise or on-prem refers to physical computers and servers in your own office building. This is how computing has traditionally been done. Let's say you need a server, so you go out and you buy that server. You then need to install it, secure it, maintain it, and eventually decommission and replace it. All of which takes a lot of time and a lot of money. It also isn't very scalable. Let's say you develop a popular fitness app. Day to day, you have enough power to run your app. However, when January comes around and everyone joins the gym as part of their New Year's resolution, you predict you will need 3 times the computing power to cope with demand. So now you have 2 choices. 1, do you stick with the server and potentially overwhelm the system? Or 2, do you commit to purchasing additional expensive hardware to cope with the demand of a relatively small amount of time. It's a difficult decision to make, and it highlights a number of problems with on-premise solutions. Luckily for us, the days of relying on on-premise servers are coming to an end. Cloud computing can solve all of these problems and much, much more. So what is cloud computing? Cloud computing, at its core, is moving your physical server into someone else's office. At its most basic level, that is what cloud computing is. I hate to disappoint, but there's no magic cloud or data center in the sky. So what do I mean by moving your physical server into someone else's building? The idea behind cloud computing is we can pay a company to provide us with all of the computing power we need on a pay-as-you-go basis. This comes with a number of benefits. The upfront cost is dramatically reduced. We don't have to spend thousands upfront, we just pay for what we use. Because the cloud provider owns the server, that means we don't have to install, maintain, or secure that hardware. That is all taken care of by the cloud provider. There's also the benefit of scalability. Take our fitness app, for example. With cloud computing, it's easy to add extra bandwidth, hardware, and resources as and when we need it. And once the January buzz has passed, we can easily scale back. Another benefit is security. These companies often have much higher budgets to protect your assets. Also, when it comes to uptime, data integrity, and so on, most cloud providers have multiple data centers. This ensures minimal downtime and maximizes data redundancy. So now we have a general idea of what cloud computing is. Now let's have a look at how it works. Cloud providers have invested in huge data centers that contain racks and racks of servers. Instead of renting out each server to customers, they use virtualization. Virtualization allows the cloud provider to be extremely efficient and flexible with their resources. Let's take one server for example. This server could have multiple virtual machines running. The virtual machine then has its own CPU and memory resources, its own storage, and its own operating system. The virtual machines are also connected to a virtual network that contains virtual switches, routers, and firewalls. By doing it this way, it's almost effortless to start virtual machines, shut them down, and move them to another server. And all of this can be done with little to no human interaction. I've been using the term cloud provider a lot, so now let's talk about who some of these cloud providers are. There are three main cloud providers, and they are Amazon Web Services, or AWS, Microsoft Azure, and Google Cloud. When working in an enterprise, these are the ones you're likely to encounter. Although these options are very comprehensive, they also come with a very steep learning curve. In fact, people create their whole careers around just one of these providers. And I personally have friends that are doing this and are very successful in doing so. If you're just getting started with cloud, there is a much simpler option. And this is where our sponsor comes in. Linode was one of the first cloud computing providers, even before AWS was around. They provide services from Linux machines to VPNs, game servers, and much, much more. Linode makes cloud computing very, very easy, with everything being just a few clicks away. They have a really simple flat monthly fee. This means you know exactly what you're spending. Another great benefit is Linode offers 24/7, 365 phone and email support with every plan. This is invaluable when you're first getting started. This support service will usually cost you quite a bit extra from other providers. So, to get you started, the team at Linode are giving you all $100 of free credit to start spinning up machines and learning about cloud computing. Use the link below in the description or go to linode.com/certbros to get your free credit. Okay, so that was a general look at what cloud computing is and how it works. Now let's look at some of the cloud computing services that are available to us. Cloud computing can be split into two categories: private and public. Private clouds describe everything we have already discussed: virtualization, automation, scalability, and redundancy, But this is all owned and controlled by one organization for their own personal use. For example, an enterprise might build its own private cloud for its in-house development team to use. Public cloud refers to public-facing companies that offer cloud computing as a service. Companies such as Azure, AWS, and Linode are all public cloud companies. The public cloud can also be categorized into different types of services that are available. I'll go through some of the most popular ones. They are Infrastructure as a Service, or IaaS, Software as a Service, or SaaS, and Platform as a Service, or PaaS. Let's start with Infrastructure as a Service. This is probably the first thing that comes to mind when talking about cloud computing. It's taken traditional computing, such as your computer, switches, and routers, and hosting it in the cloud. You can create, or spin up, as is often described, virtual machines in a matter of minutes. You have control over the hardware specs, storage space, the operating systems, and all of the applications you install, just like you would a normal computer. Next, we have Software as a Service, which you may not know, but you use all of the time. SaaS gives you access to the software or application only. The cloud provider takes care of all of the hardware, the operating system, and everything else behind the scenes. Gmail, Office 365, Dropbox, and Salesforce are all considered software as a service. You have access to the application, but nothing behind the scenes. Lastly, we have Platform as a Service. Platform as a Service focuses on providing a platform where developers can build, deploy, and scale their applications. It does this by providing on-demand, purpose-built environments without needing to think about all of the infrastructure behind the scenes. Examples of Platform as a Service is Azure App Service and Google App Engine. Okay, so that was the theory. Before we end this video, I want to show you a quick demo of spinning up a cloud-based virtual machine. I'm going to be using Linode for this example, but the concepts are pretty much the same for all providers. So the first thing you need to do is click on the link in the description and sign up to Linode. This will give you $100 free credit to play around with. Once you sign in, you can click the Create Linode button here in the center. Then we just need to choose your operating system. Then the region. So London, UK will be closest to me. And then we just need to choose the plan. I'm just going to go with the basic 4GB plan. Scroll a little bit further down and it asks us to set the root password. So I'll just type something in here. And if you want to, it gives you the option to add SSH keys, attach a VLAN, and set backups. But I'm just going to go ahead and click Create Linode. Then it takes us to the provisioning screen, and after a few minutes, this should change to running. And after just a few minutes, we can see it's running, and you now have your very own cloud computing virtual machine. You can open up the console by clicking this button at the top right. And once it loads, go over to the Glitch tab, where we can log in using the password we set. And just for a bit of fun, I went to the marketplace and spun up a Counter-Strike Go server with just a few clicks. Now please don't judge me, I haven't played this game in years. That's it for cloud computing. You should now have a solid understanding of what it is and the benefits of using it. This video is part of the full CCNA course. If you like this video, then check out the full course in the description. Don't forget to like, comment, and subscribe. The support from you guys really does help this channel grow. Other than that, thank you for watching. Hey, what's up guys? Welcome to Cert Bros. In this video, we're going to be looking at the domain name system. So the domain name system is more commonly known as DNS. DNS plays a very important role in modern day networking. It's the unsung hero that allows us to use the internet in the simplest way possible. Without DNS, our connected lives would look very different. Let me show you what I mean. The world is full of web servers. Almost 2 billion websites exist today. Websites such as Facebook.com, YouTube.com, and of course, everyone's favorite, certbros.com. The problem is, web servers like these don't use names like certbros.com. No, web servers actually use IP addresses. This becomes an issue. Being the small-minded humans that we are, we can't process large amounts of IP addresses very easily. Humans are much better at using domain names, such as certbros.com. But web servers can only understand IP addresses, such as 160.153.137.40. Can you imagine trying to browse to websites using the IP address alone? This is why we need something that sits in between us, something that will convert our domain names to IP addresses, almost like a translator. This is where DNS comes in. DNS will take our domain name and then translate or resolve it into an IP address. Let's see how this works. Okay, so this is your computer, and you want to go to your favorite website, so you type www.certbros.com. Remember, web servers do not work with domain names, so your computer needs to translate this into an IP address. The first thing it does is check the local cache both on the computer and the browser. There's also a local configuration file that's checked. If there are no cache entries, your computer will send a query to something called a DNS recursive resolver, asking for an IP address for certbros.com. The DNS recursive resolver will most likely be managed by your ISP. You can change this to a third party such as Google DNS, or even run your own internal DNS resolver. Once the DNS resolver receives your query, it checks its cache. If it can't find an entry for certbros.com, it will send a request to another server. This is called a root server. A root server is at the top of the DNS hierarchy, and is the first step in resolving certbros.com to an IP address. There are hundreds of root servers around the world, but they all use one of 13 IP addresses. The job of a root server is to provide the details of top-level domain servers. A top-level domain could be .com, .org, .net, etc. In this example, the root server will refer us to the top-level domain server for .com. So then we query the top-level domain server for certbros.com. A top-level domain server, or TDL for short, is a server that contains information for domains with a specific extension. In this example, we've queried the .com TDL server. But the TDL still doesn't know the IP address we need. It will, however, know the location of the authoritative name server. We then send our query to the authoritative name server. This is the last step of the DNS lookup. With a bit of luck, the authoritative name server will have a record for certbros.com, and it will return the IP address to our DNS resolver. The DNS resolver will then send this IP address back to our computer, and now, with the IP address, our computer can then speak directly to the web server. And all of that happens in a blink of an eye. So next time a web page is taking a moment to load, just think back to all of these requests happening behind the scenes. So normally, if you're running a packet capture while querying DNS, you will only see the request to the DNS resolver and the DNS resolver's response. The root, TDL, and authoritative name server queries are only ever seen from the perspective of the DNS resolver. But in this video, I want to show you the whole process live and in action. The way we can do this is by setting up our own internal DNS resolver. So here is my host computer, and it's also a DNS server as well. It's a Windows 2019 server with DNS installed. If I open PowerShell and I type ipconfig/all, we can see at the bottom the DNS is set to ::1 and 127.0.0.1, which hopefully by now you know is our local loopback address. The first thing I'm going to do is open Chrome and Wireshark. To capture this entire process, I need to be very specific in how I go about this. Because DNS is so darn efficient, I need to make sure that there are no cached entries anywhere. So I need to first clear my browser cache. You can see already I have chrome://net-internals/#DNS open. This page lets us clear Chrome's DNS cache. So after I click that, I now need to clear my computer's DNS cache. I'll open PowerShell again, type ipconfig/flush DNS. Hit enter, and now my computer's DNS cache has been cleared. Now because this is also a DNS server, I need to take another step, which is to clear the DNS server cache. To do this, I type clear-DNS server cache. But before I press enter, I need to get everything ready. DNS is very, very quick to start caching entries, and if I let it, it will start to cache TLD servers. So I'll open another tab in my browser and type www.certbros.com. But I won't press enter just yet. Next, I'm going to start our Wireshark packet capture. While that's running, I'm ready to clear the cache and browse to the website. So I'll open PowerShell backup. I'll move it over so we can see the packet capture. Now I'll press enter to clear the DNS server cache. It will ask me to confirm by typing Y. As soon as I press enter, I want to load the website to avoid any chance that DNS will start caching servers. So I'll hit enter in PowerShell and straight away load certbros.com in the browser. And as the website starts to load, we can see lots of traffic in our Wireshark capture. As soon as we start to see the web page, we can stop capturing traffic. I'll make Wireshark full screen so it's easier to see. There's a lot of information here, so the first thing we want to do is filter the capture to only show DNS traffic. To do this, I'll simply click on the display filter at the top of the screen and type DNS. Now we only see DNS traffic. Because this computer is our DNS resolver, the first entry we see is going to be the query to the root server. We know this because the destination IP address is one of the 13 root server IPs. If we open the transport layer information, we can see that it's sent using UDP to a destination port of 53, which is the well-known port number for DNS. If we close the transport information and now open up the DNS information, then select queries, we can see our request for www.certbros.com. The request is for an A record. An A record is an IP version 4 address for a domain. If we were trying to find the IP version 6 address, it would be an AA record, also known as Quad A. Okay, so now if we look down the capture, we should see the root server reply. If we select the reply, we can see the ports have been reversed and now the source port is 53. We can still see the query for certbros.com, but now we have some more information. Under authoritative name servers, we have a list of the .com top-level domain servers, or TLDs. Additional records show the IP addresses for these TLD servers. The top IP address is 192.5.6.30. If we take a look at the capture again, we can see we sent a request to the top-level domain server for certbros.com. Hopefully, this process is starting to look familiar to you. If we then scroll down, we can find the reply from the TLD server. The query is still there, and the response is listing 2 authoritative name servers. Again, additional records show the IP addresses. We are now at the last step of this process. A bit further down, we can see we sent one last query to the authoritative name server at 173.201.69.22. Again, we are asking for www.searchbros.com. The reply is just below. Here we see the query and finally the answer, which is the IP address for searchbros.com. If I change the display filter at the top of the screen to ip.addr == and then the IP address 160.153.137.40, we can see the conversation between this computer and the web server hosting searchbros.com. Now that our computer knows the IP address for searchbros.com, it's going to cache this for future use. If we open PowerShell, type ipconfig/display DNS, we can see an entry for www.searchbros.com and the associated IP address. As well as our local computer, the browser and the DNS server will cache this entry to make it easier to find in the future. This video is part of the full CCNA course that can be found in the description, so please feel free to go and check that out. That's it for DNS. If you liked this video, don't forget to give it a thumbs up, comment, and subscribe. The support from you guys really helps this channel grow. Other than that, thank you for watching. Hey, what's up guys? Welcome to CertBros. In this video, we're going to be talking about computer networks. Okay, so what is a computer network? Well, first, let's break it down. What is a network? The definition of a network is a group or system of interconnected people or things. So, it would be fair to say a computer network would be a group or system of interconnected computers, right? And that's exactly what it is. A computer network is anything where more than one computer is connected to each other. Traditionally, a computer network would consist of desktop computers, servers, printers, etc. But these days we live in a connected world. We still have desktops, servers, printers, but we now have a vast number of smart devices connected to our networks as well. Most of you will have a mobile phone, maybe a tablet, security cameras, even smart lights are found on networks these days. And the list really does go on and on. So let's take a look at some basic networks and we can see what they look like. First, one that should be familiar to most of you. Here we have a switch, a router, a wireless access point, a desktop, and a phone, all connected to the same network. This is a pretty common home setup. It's worth noting that in most home networks, the switch and wireless access point will be built into the router. Generally speaking, any network in a single area is called a local area network, or LAN. The LAN is usually connected to the outside world using a socket in the wall that your internet service provider has installed. This socket connects you to something called the wide area network, or WAN. The purpose of a WAN is to connect separate local area networks together. The most obvious example of a WAN would be the internet. However, businesses might have private WANs to connect multiple sites together. So now let's look at a more business type network. So we have all of our office computers, and these would usually plug into a wall or floor socket. These sockets will have cables either running through the floor or the ceiling back to a special room called a wiring closet. This room might also be called a patch room or a server room. In the wiring closet, all of these devices will connect to a stack of switches which are mounted onto racks. Depending on the size of the network, there may be multiple wiring closets, which all connect to each other, say for example on different floors. Keep in mind though, this has been simplified to give you a general idea. Lastly, we'll look at another type of network that might not be so obvious. Now, I said before, I'm sure you all have smartphones of some sort. Now, these phones generally have internet access via 3G, 4G, and even 5G. Well, you can think of these as basically a giant wireless network for your phones. Somewhere close to you, there will be a giant tower that allows you to connect and get internet access. The closer you are to these towers, the better the connection is likely to be. So these are just some common network types and really just an introduction to some basic network devices. So the next logical question is, why? Why do we need networks? Well, let's imagine life without networks for a second. If we want to print a document, we would need to directly connect a printer, which is fine. But what if we have multiple computers? We would need multiple directly connected printers, right? Which isn't so fine. The beauty of a network is we can share resources. If I have a file and I want to send it to someone, I can. They can also share the file with everyone else. We can have shared printers that everyone can use. We can even have servers that could store these files for us. Of course, file sharing and printing is just one example, but this could be pretty much anything. And all of this even before we start talking about the internet, which by the way is just a giant network. With the internet, we can search for anything we want. We literally have the world's knowledge at our fingertips. We have email. We can message our friends. We can use hosted computing, telephone calls over the internet, and of course, awesome YouTube content. So networking has changed the world and how we live in it. It's a topic I still get excited about, and there's no shortage of new things to learn. We'll go over a lot of this in more detail as we go. This video is part of our full CCNA course, which can be found in the description. So please feel free to go and check that out. If you like this video, don't forget to like, comment, and subscribe. Other than that, thank you for watching.
Hey, what's up guys? Welcome to Cert Bros. In this video, we're going to be talking about Network Address Translation, or NAT for short. We're going to be looking at the problem, so why NAT is needed. We're going to be looking at the solution, so why NAT helps to solve that problem. And we're going to be looking at the 3 different types of NAT. So, to understand NAT, we must first understand the problem that NAT helps to solve. To do this, we have to take a look back in time, all the way back to the 1970s, 1980s, which in terms of technology seems like centuries ago. Way back then, a group of people sat back in their chairs and they said, "We've done it. We've created all the IP addresses we'll ever need, and we shall call it IP version 4. Now, if you were sat in that same room, you'd probably agree. See, back then, no one would ever have guessed how big the internet would grow. In fact, IP version 4 creates over 4 billion addresses. And given that the internet was not really designed to be used by everyone, this was a massive number. But as the internet grew and more devices required addresses, we quickly began to run out. Luckily, some very clever people caught onto this early and devised a plan to help prolong the life of IP version 4 until they could come up with a new version, which we know as IP version 6. So, the solution they came up with, can you guess what it was? That's right, private addresses. Bet you thought I was going to say NAT then. No, private addresses were developed to help prolong the life of IP version 4. What these people did was create 3 groups of addresses and called them private addresses. These addresses can be used over and over again. So what we're left with is a small group of addresses that can be used billions of times, trillions even, over and over and over again. There is one slight catch though. These addresses can only be used inside an internal network. They are not allowed over the public internet. Let's see an example. Let's say this is your home. Here is your computer, here is your printer, and here is your tablet. They're all assigned a private address from the 192.168.0.0 group. This works fine communicating with each other. They get along pretty happily. But if these addresses can't access the public internet, does that mean they can't do anything outside of their internal network? Let's add a router into the equation. When you sign up with an ISP, they will give you a public address. This can be used on the internet, but usually they only give you one. So with all these devices, how can we use just one public address? This is where NAT comes into play. NAT converts private addresses to public addresses. Let's take a closer look at how this works. We will simplify this to make it easier to understand. First, we'll look at PAT, which stands for Port Address Translation, also known as overload. This is by far the most popular version of NAT, and is what you'll be using in your home. When your computer sends data to the router takes a look at it. It looks at the source address, the port number, the destination address, and the destination port number. Now, the port number is very important here. Not only will it distinguish which device the data belongs to, but it also tells the device which application that data belongs to. Very simply, the router swaps out the private source address and port number, then swaps it for a public address and port number. The port number will often stay the same, but if it's already being used, then the next available one will be selected. To keep track of which public addresses belong to which private addresses, the router builds a NAT table. This table matches the private address and port number to the public address and port number. Once the router swaps the addresses and adds it to the table, it rebuilds the data and sends it on its way. When the data comes back, the router again looks at the addresses. The source address is now the address where it came from. Some web server somewhere doesn't really matter. The destination is now the public address and port number. The router looks at this and checks the destination against the NAT table. If it finds a match, the router will swap out the public address and port number for the private address and port number. It will then send it on its way. Once the computer has the data, the port number will tell which application to send it to. If you're searching the internet, for example, it can even tell which tab to send that data to. Dynamic NAT. Dynamic NAT actually goes against everything I've just said. It doesn't save addresses because it's a one-to-one mapping of addresses, but it's still a type of NAT nonetheless. For dynamic NAT, you need to manually create a pool of public addresses. This would require you to purchase these public addresses from your ISP. Our pool will be represented by this bucket, because I didn't really know how to draw a pool. Apart from that, dynamic NAT works in pretty much the same way. When data comes in, the router looks at the source and destination address, swaps out the source address for the first available public address from that pool, and then it sends it on its way. When the data comes back, it again looks at the source address, then looks at the destination address. If it finds a match in the NAT table from the destination address, it swaps it out for the private, and then sends it on its way. After this is done, the public address will return to the pool, ready to be used again. Lastly, we take a look at static NAT. Static NAT requires you to manually type in the entries to the NAT table. You tell the router which private address and port number translate to which public address and port number. Once this is done, it works just like the other two versions. When the data comes in, it checks the NAT table for the source address. When it finds a match, it swaps the address for the public address and then sends it on its way. When the data comes back, it checks the destination address against the NAT table, swaps the public for the private address, and again sends it on its way. This version of NAT is mostly used for public servers like web servers, for example, where the port will always be 80, for example, for HTTP. So, NAT translates private addresses to public addresses. It does this by using a NAT table to keep a record of these translations. Very clever, but pretty simple. If you enjoyed this video, and we hope you did, please give us a thumbs up, comment, and subscribe. These videos are for you. So if you want more, let us know. That's it for network address translation. Thank you for watching.
Hey, what's up guys? Welcome to SerPros. In this video, we're going to be talking about firewalls. What they are, what they do, and also the difference between traditional and next-gen firewalls. So first, what is a firewall? If you drive or you're into cars, then you may be familiar with the term. If your engine explodes and catches fire, there is something called a firewall that separates and shields you from the burning hot flames. And network firewalls work in the same way. Let's take this basic network as an example. We have two hosts, a switch and a router. Because you, as a company or as an admin, have control over these devices, policies, antivirus, etc., it's reasonable to consider this as a trusted network. But we have zero control over the devices and networks outside of our own. So it's fair to consider these as untrusted networks. Now, while most of the world is full of good-intentioned, trustworthy people, there are a huge number of bad guys out there looking to take down your systems and get their hands on your hard-earned money. With routers generally having minimal security features, you can quickly be at the mercy of the attackers. This is where firewalls come in. Firewalls are designed to shield and protect our trusted networks from the untrusted. The idea is that a firewall will block all of the bad traffic from the attackers, while at the same time, they'll allow normal flow for good traffic. So let's look at how firewalls achieve this. Most firewalls, by default, block everything. It doesn't matter if it's traffic leaving the network or traffic entering the network. Everything is blocked. The way we allow traffic to pass the firewall without being blocked is by adding something called firewall rules. For example, we may add a rule where the source is host A, the destination is any, because we're not going to add a list of every possible web server, and the port is HTTP or HTTPS. And we'll set the action to allow. The exact firewall rule format will vary from vendor to vendor. Now, when host A sends traffic, the firewall will see this and think, are you from host A? Yes. Are you going to any IP address? Yes. Are you using port HTTP? Yes. Okay, you are allowed. And it lets the traffic through. If host B tries to send traffic, the firewall checks its rules, sees that there are no matching rules, and blocks the traffic. So now let's add a rule for host B. Source, host B. Destination, any. Port, this time we'll choose any port. Not a recommended rule, but it will do for the sake of the example. Action, allow. Now both host A and host B can send traffic through the firewall. So that's traffic leaving the network. But what about traffic entering the network? Well, it's a good idea to block all traffic from external sources. The only exception is in special cases where you need to open up access for, say, VPN servers, email servers, and web servers. But if you do this, they should be tightly controlled by the firewall rules. But this poses a bit of an issue for us. Let's say we request a web page. The firewall checks our rules and allows the traffic through. At some point, that web server is going to respond, right? But if the firewall doesn't allow inbound traffic, what does it do? Well, most firewalls are something called stateful firewalls. Stateful firewalls monitor active connections. This means that once outbound traffic has been allowed, the returning traffic is then accepted. This is great because we don't need to add separate outgoing rules and separate incoming rules. Okay, so everything we've just discussed so far is known as a traditional firewall. It mostly uses firewall rules to block or allow traffic, based on a number of things like IP address, port number, etc. Now, next generation firewalls take the same methods, but then they enhance them with more in-depth security features. Quick warning, there are a lot of buzzwords out there, and next-gen firewall is definitely one of them. Different vendors will have slightly different meanings and features to what a next-gen firewall is or what theirs does, but generally speaking, this is what a next-generation firewall should include. Application level inspection. So the firewall can identify and block risky application traffic. Intrusion Prevention Systems, or IPS. IPS will inspect the contents of the traffic and look for patterns or signatures. It's looking for malicious or malware-related traffic. IPS can also detect anomalies and unusual traffic. External threat intelligence. Next-generation firewalls can update themselves from external threat intelligence sources. So if a brand new attack has been identified, the vendor can update the firewall's threat intelligence to be able to identify this new emerging threat. There are a huge number of features that firewalls can offer. Things like URL filtering, email scanning, data loss prevention or DLP, and the list goes on and on. Firewalls that have features like these are often known as UTMs, or Unified Threat Management. The idea is you have a single appliance that unifies all of these security features. So that is how a network firewall works. But you may have seen another type. Computers can also have software-based firewalls. For example, the Windows firewall is built in and it uses the same rule-based methods, such as port, destination, and source IP address. So you might be thinking, why have a network and an endpoint firewall? I like to think of it like a house. If you lock all of your internal doors, would you be happy to leave the front door wide open and let the bad guys wander your halls? Probably not. Having a firewall both on the network and the endpoint is important when creating a layered security posture. If something gets past the network firewall, the endpoint firewall is there to catch it. Also, what if the attack comes internally? The network firewall doesn't see the traffic, but the endpoint firewall does. That's it for firewalls. This video is part of our full CCNA course, which can be found in the description. So please feel free to go and check that out. If you liked this video, don't forget to give it a thumbs up, leave a comment, and subscribe. The support from you guys really helps this channel grow. Other than that, thank you for watching. Hey, what's up guys, welcome to Cert Bros. In this video, we're going to be looking at syslog. Meet Bill. Bill is a network admin, and it's his job to manage and troubleshoot the network. Part of that job means searching through log files when things go wrong. This network is pretty small, so it's easy to keep on top of all of the log information. The problem is, as the business grew, so did the network. It got bigger and bigger and bigger. Now it's nearly impossible to keep on top of all of the network log information. So Bill decided to find a solution, and he discovered syslog servers. A syslog server allows all of his network devices to send their log information to one centralized place. The log messages will be sent on UDP port 514 to the syslog server. From here, he can manage, search, and archive all of the log information. Okay, so I hope you liked my little story there. Using a syslog server allows us to centrally manage our log information. Why would you want to do that? Well, there are a few reasons why. First, log information is very important when troubleshooting problems. Let's say a user reports a network outage. You can go through all of the log information to see if there were any problems. Another benefit of storing log information in a central place is data retention. Cisco devices, by default, store log information in RAM. This means when a device reboots, the logs are erased. Other vendors may write log information to disk, but network devices tend to have a small amount of storage available. Keeping all of your log information in one place allows for easy archiving. Okay, so now we know what a syslog server is and why we use them, let's look at some log messages. This is a syslog message. It will probably look familiar to you by now. It's the messages you see when configuring routers and switches. It may not seem like it straight away, but these messages follow an industry standard. This makes it easy to correlate logs from different vendors. The first part is the timestamp or sequence number. On Cisco devices, you can choose which one you want to use. The next part is called the facility. This shows the source of the message. Next, we have severity. This shows you how urgent the log message is. Then we have something called the mnemonic. This is a code to identify the message. And finally, we have the description, which contains the log message. There are two key bits of information here that we need to look at further. These are facility and severity. First, let's look at the facility. Here is a table of all available facilities. Remember, the facility represents the process that generated the message. Because syslog was adopted early by Unix systems, these facility codes are mostly Unix-based. For example, if a Unix kernel generated a message, the facility would be kern. If an authentication message was logged, the facility may show auth. You'll notice there aren't many network-related facilities. At the bottom we have 16 to 23 local use. These are undefined custom values that are generally used for network devices. So the next and probably the most important bit of information here is the severity. Syslog has 8 severity levels, ranging from 0 to 7. The top is the most urgent, so severity is 0, and the bottom is the least urgent, which is 7 for debug messages. This is important because you likely don't want to send all log messages to your server. You can choose which messages are sent based on their severity. This way, your server doesn't get clogged up with messages you'd rather not see. Now, unfortunately, this is one of those tables you're going to have to memorize for your CCNA exam. You need to know not only the severity levels, but which order they're in. As with most of these things, mnemonics come to the rescue. A popular one is every awesome Cisco engineer will need ice cream daily. Another one I found was Ernie always cries even when no one is dying, which made me laugh probably more than it should. Okay, so now we've been over the theory, let's see it in action. Here is my computer. I'm running a program called Kiwi Syslog Server. There are lots of different syslog servers out there. Some are free, some are paid. I'm using this one because it's free for up to 5 devices. As you can see, nothing is going on here. That's because we haven't configured anything. The first thing I'm going to do is go to File, Setup, scroll down to Inputs, and if you're doing this at home, you will need to input the IP address of the device you want to receive syslog messages from. I've already entered the IP address of my Cisco router. After you've done that, just click OK. Our server is now ready to receive syslog messages, but still, nothing is happening. We need to configure the router to send syslog messages to the server. So I'll open the router, and you'll already see some familiar looking messages. These are syslog messages showing when the router boots up. You'll notice the timestamps are completely wrong, so we'll need to fix that. It's recommended to use an NTP server to sync our time correctly, but in this example, I'll just set the time manually. I'm already in privileged exec mode, so I don't have to type enable. Now I'll type clock, ? We only have one option here, and that is to set the clock manually. If I type clock set ? We can see that it asks for the hours, minutes, and seconds. It's 8:22, so I'll just type 08:22:00. It then wants the day and the month. I'll type 07 September. And if I press the question mark one more time, it asks us for the year. So I'll type good old 2020. When we hit enter, we're greeted with an information message telling us the clock has been changed. Now the time is set, we need to make sure it's included in the syslog messages. To do this, we need to enter global configuration by typing configure terminal. Now I'll type service ? Lots of information here. The two main ones are sequence numbers and timestamps. Remember earlier when I said syslog messages can either have a sequence number or a timestamp? Well, this is where we choose. I'll choose timestamps. And if I type ? We have the option for debugging and log messages. We want to change the log messages, so we'll type log. Again, ? And now we get the choice between date time or system uptime. Of course, we want the date time, so we type date time. The last few options here, if we choose MSEC, then it will include the milliseconds in the timestamp. This can be very handy when troubleshooting. Hit enter, and now the timestamps are set. We're now ready to tell the router to send log messages to our syslog server. First, we tell the router where to send the logs. We do this with the command logging and then the IP address of our server. In my case, it's 192.168.0.1. Now we need to choose which logs to send. If I type logging again, but this time with a question mark, we'll see lots of options. The one I want is trap. The description says set syslog server logging level. So we type logging trap, and to see the levels, we type a question mark. Here we choose the severity of logs we want to send. In this example, we're going to choose informational. An important note here is that whichever level you choose, it will send those logs as well as the logs with a higher severity. So we've chosen informational, which is level 6. The router will send all log messages with a severity of 0 to 6. The last thing I need to do is configure the IP address. So I'll type interface, fast Ethernet, 0/0, then IP address 192.168.0.254, and a subnet mask of 255.255.255.0. And I'll bring the interface up by typing no shutdown. Now our router is configured and waiting to send some log messages. We just need to generate some logs. To do this, I'll just exit here, go into another interface, and this time it will be fast Ethernet 0/1, and type no shutdown. Our router will generate some logs saying the interface is now up. I'll now shut it down again to generate a few more. If we now go back to our syslog server, we can now see our router's logs. From here, we could search, filter, and correlate all of our log messages. This video is part of the full CCNA course, which can be found in the description, so please feel free to go and check that out. If you like this video, don't forget to give it a thumbs up, leave a comment, and subscribe. The support from you guys really helps this channel grow. Other than that, thank you for watching.
Hey, what's up guys? Welcome to Cert Bros. In this video, we're going to be looking at multi-area OSPF. Okay, so multi-area OSPF. This is the expansion to the single area OSPF video. If you haven't watched that video and you're not familiar with OSPF, then you're in the wrong place. Go check that video out, give it a like, leave a little comment, and come back when you're done. Okay, so if you have watched that video, then our Little 5 router network should look familiar. You will also know that OSPF floods link state information to all neighboring routers using LSAs. Each router then takes those LSAs and builds a link state database. They then run the SPF algorithm. Finally, the routers choose their best routes based on the route cost. And that's fine in our teeny tiny network, but let's think bigger. Imagine you have 100 or 500 or even 1,000 routers. Now, first of all, it's highly unlikely your network will look like this. But let's just take a second to admire the beautiful symmetry of this network. Okay, so now we've taken that in, what do you think will happen when using single area OSPF in this massive network? Well, we're going to run into a few problems. Problem number 1, the link state database will be huge. Every router will have a copy of the same LSDB filled with information about every router and every link within the entire network. Probably information that it doesn't even really care about. All of this information can even start to fill up the disk space. Problem number 2, not only will the database be huge, so will the routing table. With a route to each subnet, this means every time a packet comes in, your routers may need to search through hundreds or even thousands of routes before it finds the right one. This will also impact the disk space and even the processing power of the router itself. Issue number 3, updates everywhere. Anytime a link or router is changed, disabled or enabled, cables are pulled out, cables are plugged in, updates are flooded throughout the entire network. Not only that, but each router will have to rerun the SPF algorithm every time an update is sent. Introducing OSPF multi-areas, the solution to all of our OSPF problems. Using multi-area OSPF will reduce the size of our link state database, summarize our routing tables, and it will contain update messages to a single area. The price we pay for all this OSPF goodness? Complexity and a little extra time. Let's take a closer look at how this actually works. But first, let's mix it up a little and use a brand new network diagram. So we're going to split these routers into areas.
An area is simply a group of routers. Now it goes without saying, this is a very simple 5-router network, so no need for multi-areas. However, for the sake of simplicity, imagine each area containing multiple routers. Generally speaking, it's recommended to have less than 50 routers in an area, but there's no real hard limit. It all really depends on the processing power of your routers. When it comes to designing your OSPF areas, there's some planning that needs to be done. First of all, you need to start with Area 0. This is known as the backbone area. Every other area must join to the backbone area. Secondly, to benefit from OSPF areas, you need to plan your subnetting. As you can see here, Area 1 has all of the 10.something networks, and Area 2 has all of the 172.16 something networks. This really is the key to successful OSPF areas. Let's take a look at how we can summarize our routes. Router 2 and Router 3 are known as Area Border Routers, or ABRs. These are special routers that have interfaces in 2 or more areas. This gives them the power to summarize routes from each area. For example, Router 2 can take all of the 10.something networks and say, hey, any packets to the 10.0.0.0 network, send them my way. Router 3 also says any traffic for the 172.16.0.0, leave it to me. And they both send a single route to Area 0. Router 2 and Router 3 will also summarize Area 0's subnet to Area 1 and 2. This route summarization instantly wipes out all of our OSPF problems. The routing table is drastically reduced because huge subnet chunks are summarized into a single route. As a result of this, there are far less LSAs flying around, reducing the size of the LSDBs. The updates are usually contained within their own areas as well. For example, Router 1 doesn't care if the 172.16.5.0 link goes down. All it knows is Router 3 has all of the 172.16 subnets. So it just sends it over and lets Router 3 deal with it. This stops the need to run SPF every time a change occurs, unless that change happens within the router's own area. The exception to this would be if the ABR interface went down itself. It would then need to tell the other areas that something terrible has gone wrong. So after some careful planning and a little extra time, we now have a scalable OSPF network using multiple areas. Before finishing, we've already looked at ABRs, but there are some others. Backbone routers. These are all routers that are in, or partially in, the backbone area. So in this case, Router 1, Router 2, and Router 3 are backbone routers. Area border routers. We've already looked at these, and they are routers that connect to more than one area. Router 2 and Router 3 are ABR routers. Internal routers. These are all routers within a single area, but not the backbone area. Router 4 and Router 5 are known as internal routers. Lastly, Autonomous System Boundary Router, ASBR. These are routers that connect to other non-OSPF routing protocols, such as BGP or EIGRP. For example, this may be your edge router connecting to the public internet or another autonomous system network. That's it for multi-area OSPF. With a bit of planning and some extra time, you really can scale up OSPF far and wide. If you like this video, remember to like, comment and subscribe. It really does keep these videos coming. Thank you for watching. Hey, what's up guys? Welcome to Cert Bros. In this video, we're going to be looking at STP optional features, port fast and BPD UGuard.
If you've watched the video on STP, then you'll know the biggest problem with 802.1d is the conversions. The reason for this is the time it takes to go from a non-forwarding state to a forwarding state. So, just as a reminder, a port needs to pass through the listening and learning transitional states and stay there for 15 seconds by default before it can enter a forwarding state. I briefly mentioned on the STP video that this doesn't only affect ports connected to switches. If you've ever plugged a computer into a real Cisco switch or even used a packet tracer, you may have noticed that the port doesn't turn green straight away. It turns orange and stays there for a bit. This is because the port is going through these states. First it enters the listening state for 15 seconds, then the learning state for 15 seconds, then finally it enters a forwarding state where traffic can start to pass through. The problem with this is most computers these days boot up in less than 30 seconds, or you might even plug in a laptop that's already switched on. Then when the internet's not working, you might start running ipconfig and trying to troubleshoot why the internet's not working. Part of this troubleshooting might even be unplugging the cable and then plugging it back in, starting the whole process again. This is where PortFast comes in. PortFast pretty much just says, let's get rid of all this and essentially disables STP altogether. This lets the port start forwarding as soon as it's plugged in. Great, but STP wasn't just created for a laugh. No, it was created to stop switching loops, so disabling it can be dangerous. You must use PortFast with caution. What happens if Brian from down the hall rocks up with his switch, takes an Ethernet cable and plugs it in? With STP disabled, you run the risk of creating switching loops, and we've all seen the effect that this has on the network from the STP video. You'll remember that switches will send BPDUs to negotiate a root bridge. When Brian's switch sends a BPDU to our switch with no protection, it will accept it and probably cause a loop. But if the switch has BPDU guard enabled, then this protects us from these kind of situations. The switch will see the BPDU, realize it's connected to another switch, block the port, and put it into a funny little state called error disable. I say it's a funny little state because it's not always immediately obvious when looking at the interface status that it is in an error disabled state. You'll see what I mean in a minute. Okay, so let's quickly go over the configuration. PortFast and BPDU guard can be enabled with only one command each. First, let's see what happens when we don't use PortFast. Here's our switch. If we do a quick show spanning tree command, we can see there is no connections at the moment. If I plug in a computer, the port comes up. And if we run the same command, we can see the interface is in a listening state. It will stay here for 15 seconds, but I'll speed this up. If we run the command again, we can see it's in the learning state. Again, it will stay here for 15 seconds. And if we run the command one more time, finally it's in a forwarding state. So let's configure PortFast on this interface. So I'll unplug the computer, enter the configuration terminal, interface fast Ethernet 01 to enter the interface configuration, switch port mode access to make sure this interface is an access port, and the command to turn on PortFast on this interface is spanning tree PortFast. When you enter this command, Cisco gives you a warning message which says, "Warning, PortFast should only be enabled on ports connected to a single host." This is reminding you that PortFast can cause potential switching loops if not used correctly. You have been warned. So that's PortFast enabled for this interface. But if this switch is for mostly access ports, then we don't want to be doing this on all interfaces, do we? What we can do instead is turn on port fast by default, then disable it on any ports that need to connect to switches. This makes sense if you have a switch where only a couple of ports connect to other switches. So we'll exit out of this interface, and the command we want is spanning tree port fast default. And again, you'll get the same warning. Okay, so let's test it. We'll exit out, run the same command, show spanning tree VLAN 1, and we'll see there's no devices connected. So I'll plug in the computer and we'll run the command again. As you can see, the interface has gone straight to forwarding. No faffing around with listening and learning states, just straight into forwarding. You're going to want to know some show commands for troubleshooting. The first one is show spanning tree summary. Here you can see if port fast default is enabled. The next one is show spanning tree interface fast Ethernet 0.1 port fast. This is a very straight to the point command and tells you if port fast is enabled on that interface. And of course, we can always check the running config and see the commands we entered. Okay, so that's port fast. Let's clear the screen and look at BPDU guard. Back to the configuration terminal. And again, we can turn on BPDU guard on a per interface basis by going into the interface configuration. And the command is spanning tree BPDU guard enable. Or if we want to do it globally, we can exit out of here and run the command spanning tree port fast BPDU guard default. Show commands for BPDU guard are pretty much the same as port fast. We have show spanning tree summary, which shows if BPDU guard is on by default. Show spanning tree interface fast Ethernet 0.1 detail. This command shows us if port fast and BPDU guard is enabled on the interface. And again, show running config to show our commands. Now I've been using the pipe command with the B to show everything that begins with the word interface. Okay, so with the configuration done, let's see it in action. I'll unplug the computer from earlier. Now I'll plug in a switch to the interface with port fast and BPDU guard enabled and see what happens. The port comes up and it will take a couple of seconds to receive a BPDU. There it is. The switch received a BPDU and disabled the port, putting it into an error disable state. Earlier, I said this state can be a bit of a funny one. That's because if I run a show IP interface brief command, then it shows the interface is down. Nowhere here does it tell you that it's an error disabled state. This could be important to remember when troubleshooting. Probably the best place to check if you think an interface could be in an error disabled state is to use the command show interfaces status error disable. This will quickly show you the interface and the reason for being in an error disabled state. There are some other reasons an interface might go into an error disabled state, but this time it's because of our BPDU guard violation. Another place to look out for this is the command show interface fast Ethernet 0/1 or whatever interface you're using. At the top, it will show the error disabled state. So to fix this, you need to first fix the cause of the problem. So let's remove the switch. Then we need to go back into our interface configuration. and issue the shutdown command, then no shutdown command. This will remove the error disabled state. To prove this worked, we will exit here and run the show interface status error disable command again. As we can see, no interfaces are showing. Now we will plug in the computer again. And if we run the show IP interface brief command, we can see that the interface is now up and it's working again. That's it for Portfast and BPDU Guard. Pretty straightforward and simple, but can be a little bit tricky to troubleshoot if you don't know where to look. If you like this video, let us know by leaving a thumbs up, commenting and subscribing. The feedback we get from you guys is what keeps the videos coming. Thank you for watching.
Hey, what's up guys? Welcome to CertBros. In this video, we're going to be looking at MAC addresses. So we're getting closer to the end of our journey through the TCP-IP model. In this video, we're going to be looking at the data link layer. The data link Ethernet standards operate here. It's also responsible for adding another type of address called a MAC address. So what is a MAC address? Well, first, MAC stands for Media Access Control. It's a unique identifier that is assigned to a network interface card, aka a NIC. And this is what a MAC address looks like. The first thing to note is that unlike an IP address, which can be changed, MAC addresses are described as being physical addresses. Think of them like they're set in stone, burnt into the NIC by the manufacturer. They are unique and cannot be changed. Well, you can spoof a MAC address. The address itself is 48 bits long, or 6 bytes. Bits and bytes are binary values. There are 8 bits in a byte, and to remember the difference, think of eating binary. You take a bite, and you will have a mouthful of bits. Anyway, the address has 2 sections. The first 24 bits, or 3 bytes, is called the Organizationally Unique Identifier, or OUI. It identifies the vendor. The last 24 bits is a unique value that was assigned by the vendor that makes this address unique. There are 3 types of MAC address. Unicast, which means a particular unique MAC address, like the one we have here. Multicast, which is a MAC address used for an application or protocol. This will be sent to all devices, but only those with that application or protocol will listen to it. And we have something called a broadcast address. Now this is sent to all devices within a network. And a broadcast address looks like this. It's all Fs. So back to our unicast MAC address. It's important to note that there is more than one way to show a MAC address, and it changes depending on where you're looking at it. Here are 3 ways to display the same MAC address. The top one is 6 groups of 2 digits separated by colons. This is typically how Linux or Apple will display their MAC addresses. The middle one is again 6 groups of 2 digits, but this time separated by dashes. This is how Microsoft display their MAC addresses. Lastly, the bottom displays the address as 3 groups of 4 digits. This is how Cisco display their MAC addresses. Although you'll likely see the bottom Cisco format when going through the exam, you need to be able to look at all 3 of these and think, that is a MAC address. Okay, so I know what you're probably thinking. We already have IP addresses. So why do we need MAC addresses? Well, let's look at an example. We have 4 computers and a switch. Switches are commonly layer 2 devices. When computers are talking to each other in the local area network, or LAN, this is layer 2 communication, and layer 2 communicates using MAC addresses. But when we leave our network, this is where IP addresses are mainly used. Routers are layer 3 devices, and they mainly focus on IP addresses to get the data to the destination. So in summary, you can think about MAC addresses as local communication and IP addresses as global communication. We'll cover this more when we go into more in-depth switching and routing topics. Before we finish this video, I will show you how to check your own MAC address at home. On Windows, you simply open up a command prompt or PowerShell. Type ipconfig/all to see your interface settings. Find your interface, and remember you might have more than one if you have a wireless interface. And look for something called the physical address. If you're using Linux or Apple, open up a terminal and type in ifconfig and look for the ether address. This video is part of our full CCNA course, which can be found in the description. So please feel free to go and check that out. If you liked this video, don't forget to give it a thumbs up, leave a comment and subscribe. The support from you guys really does help the channel grow. Other than that, I hope this helped and thank you for watching. Hey, what's up guys? Welcome to Cert Bros. In this video, we're going to be looking at FTP. FTP stands for File Transfer Protocol, and it does pretty much what it says on the tin. It's a protocol used to transfer files across a network. FTP uses a client-server model. The server hosts the files, and the client can connect, download files, upload files, delete, rename, etc. Now, depending on your age, you may have used FTP already. It was quite popular to download files from friends, download software, drivers, etc. These days, you don't see FTP used too often, but it is still used in specific cases like in network management and web development. There are a few ways you can access an FTP server. The first way is through a browser. You can simply type in the FTP server address. For example, ftp://192.168.0.8. The ftp:// tells our computer to connect to the FTP port and not the HTTP or HTTPS port. As you can see, an FTP server is pretty basic, and this may even look familiar to a few of you. It's just a list of files and directories. Now, another way we can connect to an FTP server is via the Windows File Explorer. Again, we just need to type in the address into the bar at the top of the screen. The third and most popular way to access an FTP server is via an FTP client. I'm using probably the most popular one, which is FileZilla. We just need to type in the FTP details at the top. The last two methods logged us in without any user credentials. FTP gives us the option to log in as a user or anonymously. This time we are going to log in as a user by entering the host address, username and password, and also I'll specify the FTP port number, which is 21. Now, we are warned about this FTP server not using something called TLS. This is something we'll cover shortly. Once we connect, again, we can browse directories, download, and upload files. Because I logged on as a user, I now have permission to view the home directory and all of its content. I can also view the FTP folder that we already saw, and I'll go ahead and download the file. Now, just a quick note here, FTP server permissions depend on the server itself, and this is just how I've set mine up, so each one could be different. Now that file has downloaded, I can confirm by showing the desktop, and yes, there it is. Now you've seen FTP in action, let's talk about some of the more technical details. FTP uses Transport Protocol TCP. So like any other TCP protocol, the connection starts with a three-way handshake. The client will send a SYN message, the server will respond with a SYN-ACK, and finally the client will send an ACK. Now if this process looks unfamiliar to you, I have another video showing how this works in a bit more detail. That video is called TCP versus UDP, and it's worth having a look. Once we have completed our handshake, we now have an open connection to the FTP server. FTP uses two different connections. The first one is the control connection. The control connection handles all of the FTP commands and instructions, such as GET and PUT commands. Our client will connect to the FTP server with a destination port of 21 and a randomly selected dynamic source port. So when we want to start transferring files, a new connection is opened. This is called a data connection. Now there are two different types of data connections. The first type is an active data connection. The way an active data connection is established is by the server initiating the session. It does this from a source port of 20, and it uses a randomly generated dynamic destination port. There is a problem with this method though. If there is a firewall in between our client and server, this unsolicited connection from the FTP server will likely be blocked by the firewall. This is because, by default, firewalls usually block all incoming connections unless configured otherwise. So the other, more popular option is to use a passive data connection. The way a passive data connection is established is by the client initiating the session, not the server. Randomly generated and agreed source and destination port numbers are used. Because the client initiated the connection internally, the firewall will happily let the traffic pass without blocking it. So now we've seen how FTP works, let's talk about its biggest problem. Because FTP was designed such a long time ago, it lacks even some of the most basic security features we see today, most notably encryption. This means all of our communication between the FTP client and the server is sent in clear text. That includes login credentials and files being transferred. And that is great. Not for us, no. It's great for hackers. Hackers could intercept and steal your login credentials as they're sent to the server. Here's a Wireshark capture of an FTP login. As we can see, the username and password, both of which are search bros, can be seen in plain text, so very easy for hackers to steal. So why would anyone use FTP if it has such a massive security flaw like plain text transmission? Well, to put it bluntly, you shouldn't. Instead, you should use something called FTP-S instead. FTP-S, also known as FTP Secure, is an extension to FTP, adding a layer of security. FTP-S uses TLS, which is an encryption protocol used to keep our data safe and away from the prying eyes of hackers. This is what the warning message we saw earlier was telling us about. So, an FTP-S connection would look something like this. We connect to our FTP server as before, but this time we negotiate TLS encryption to keep our data safe. Now, encryption is usually described as a tunnel, and by using this tunnel, the hackers can no longer see or steal our data as we send it to the server. And this makes hackers sad. Now, the way TLS negotiations take place and the steps involved will probably need to be covered in a video all of its own. And to be honest, it's probably out of the scope for the CCNA. So for now, just know that the negotiation takes place. Now, you may hear about another protocol called SFTP, and although the name is similar and the purpose of transferring files is the same, SFTP isn't part of the FTP protocol. It's actually part of the SSH protocol, and it uses SSH to securely transfer files. Okay, so the last type of FTP protocol I want to talk about is TFTP. Unlike FTPS, which was an extension of FTP, TFTP kind of goes back the other way. TFTP stands for Trivial File Transfer Protocol, and is pretty much a stripped back version of FTP. To keep it fast and lightweight, TFTP uses UDP port 69. It also doesn't have any of the bells and whistles of standard FTP. Features such as authentication and encryption doesn't exist in TFTP. So then, why would anyone in their right mind want to use TFTP? Well, you definitely don't want to use it over the internet. But where it can be very handy is in a local network for very basic transfers. You could use a TFTP server to quickly back up a Cisco IOS image or a configuration file, for example. Let's jump into a quick TFTP example and see how we can use this to back up a configuration file. First, we're going to need a TFTP server. This computer already has a free TFTP server installed from SolarWinds. As you can see, it's pretty basic, nothing fancy to see here. Okay, so let's say we're doing some work on this router. Maybe we're adjusting the configuration for a new implementation or something along those lines. We want to back up our current configuration. One way to do this is by using our TFTP server. We just simply type copy running-config, and then we type TFTP. It will then ask for the TFTP server IP address. In this case, it's 192.168.0.10. Then it asks us for the file name. It automatically suggests r1-config. Let's keep it as the default and press enter. We get confirmation that the file has been uploaded. Now we have our config backed up, we are free to make any changes we want. In this example, I'll just go into the config mode and change the hostname to something. And I'll hit enter a few times just to confirm the hostname has changed. Right, now let's pretend it's all gone very badly, and we need to restore our config. We can just exit config mode and type copy TFTP running config. So this is from the TFTP server to our running configuration. Again, it's asking for the IP address of the TFTP server. And then the file name to copy. Remember, this was called r1-config. Confirm the destination is the running config. And if we hit enter a few times, we can see our hostname, meaning the configuration, has gone back to normal. Now, of course, we could have just copied the startup config, but this is just one example of the things we can do with TFTP servers. This video is part of the full CCNA course, which can be found in the description, so please feel free to go and check that out. If you like this video, don't forget to give it a thumbs up, leave a comment, and subscribe. The support from you guys really helps this channel grow. Other than that, thank you for watching. Hey, what's up guys, welcome to CertBros. In this video, we're going to be looking at First Hop Redundancy Protocol, or FHRP for short. So, we've already talked about the importance of redundancy in modern day networks. We've looked at using multiple switches and how spanning tree protocol removes any switching loops. We've even looked at using multiple links and grouping them into an EtherChannel. But what about layer 3 communication? What redundancy do we have there? It's all well and good keeping local communication running, but imagine if the internet connection goes down. All hell would break loose. By only having one router, we have just introduced a single point of failure. If this router or the link goes down, then goodbye internet. So to combat this, we can introduce a second redundant router. Each router would then connect to the internet or even the corporate WAN. We add the second router to a different switch to remove a single point of failure, meaning if one switch fails, then the other still has layer 3 access. There is a problem with this setup though. Let's clear this up and add some more information. Can you spot the problem here? What does a host do if it's trying to send data to a device that's not in its own network? It sends it to the default gateway. This is the problem. Each host lists router 2 on the right as its default gateway. So what happens if router 2 goes down? Well, luckily we still have router 1. But the host still has router 2 listed as the default gateway. This is the problem. When a router fails, there is no way to automatically change the default gateway for all hosts. They will continue to try to send data to the router that failed. This is where first hop redundancy protocols come in. FHRPs allow hosts to send data to the redundant router without needing to make any changes. And the way it works is very, very clever. Here is a very brief overview before we go into some of the finer details. You configure your routers to be part of a group. The group is then assigned a virtual IP address and a virtual MAC address. This is how it works. Let's say host B sends an ARP request for the default gateway. This ARP request will be for the virtual IP. That request is sent to all devices in the network. Both routers receive this request, but only one responds. But it doesn't respond with its own MAC address. No, it responds with the virtual MAC address. Now let's say our router goes down. This is where the magic happens. When the same request is sent, our second router receives it, and knowing the other router is down, it responds to the request. Again, it sends the virtual MAC address. The host is none the wiser about which router it's talking to, it only knows the virtual IP and the virtual MAC address. But what happens if no requests are sent and the hosts just use their ARP cache? Well, when the new router takes over, it will start to send a special type of ARP message. This message is called a gratuitous ARP. This tells the switches to update their MAC address tables. This way, all devices will now use the new router. So that is a very general look at how FHRPs work. And to be honest, that could be enough for the CCNA, as it only states you should be able to describe the purpose. But let's look a little bit deeper so you can get a solid understanding. The first thing to know is that first hop redundancy protocol isn't one protocol. It's actually a term used to describe a family of protocols. Here we have HSRP, or Hot Standby Router Protocol, VRRP, or Virtual Router Redundancy Protocol, GLBP, or Gateway Load Balancing Protocol. We're going to look at each of these in a bit more depth. Let's first look at Hot Standby Router Protocol, or HSRP. HSRP is a protocol designed by Cisco, and it works in very much the same way as we've just seen. Let's bring back our network. Now remove some switches to make it easier to see. The first thing that's going to happen is the routers will start to send messages. Routers with HSRP will send and receive multicast hello messages every 3 seconds. This is used to communicate with each other. Their multicast address depends on the version. For version 1, the address is 224.0.0.2. And for version 2, the address is 224.0.0.102. They then decide which router will be the active one and which will become the standby. The active router takes ownership of the virtual IP and MAC address. The standby router simply waits until the active fails. The way an active router is chosen is based on the highest HSRP priority, and if that ties, then the router with the highest IP address. When you configure HSRP, you will select a virtual IP address to be used. This is the IP address you'll configure as the default gateway. The virtual MAC address, however, is generated automatically and it follows a specific format. The first part of the MAC address always stays the same. This is how you can identify a HSRP virtual MAC. The last 2 or 3 digits, depending on the version, shows the group ID. When you configure HSRP, you configure a group of routers. This part of the MAC address represents that group. I recommend you try to remember this format for the CCNA exam. And the last thing we need to do is assign the virtual IP address to the host's default gateway. Now that everything is set up, normal operation can resume. The routers will send hello messages every 3 seconds. This lets them know that everything is A-OK. But let's say our active router goes down. Our standby router won't receive any hello messages from the active router. The standby router then waits the hold time, which is 10 seconds by default, before leaping into action. Once the hold timer has expired, the standby router will assume the active role and then announce himself to the rest of the network. This is so the switches can update their MAC address tables and list the correct port number. By default, if our router comes back up, it won't automatically take over as the active router. It will instead become the standby. If you have a favorite router that you want to always be active, then you can enable something called standby preempt. Okay, so that is HSRP. Now let's move on to VRRP. After Cisco released HSRP, an RFC was created for a similar protocol, Virtual Router Redundancy Protocol. VRRP works in a very similar way to HSRP. There are only a few slight differences. The first difference is that the router roles are called master and backup, not active and standby. How the routers choose a master is also different. First, we need to bring in the IP addresses. In VRRP, you can assign one of the routers the same IP as the virtual IP. This makes that router something called an IP address owner. When choosing which router should be the master, the IP address owner is always preferred. If that router goes down and there are other routers to choose from, then it goes to the same tiebreakers as before. The highest priority, then the highest assigned IP address. If we now take a look at the virtual MAC address, you will see a different format. Just like before, the first part of the MAC address represents a VRRP virtual MAC, and the last 2 digits represents the group ID. Again, I recommend you try to remember this format for the exam. Like HSRP, VRRP sends messages to the network. Unlike HSRP, the messages are only sent from the master. Master routers will send advertisements to a multicast address of 224.0.0.18. These advertisements are sent every 1 second by default. If the master router fails, there is a master downtimer, which is 3 times the advertisement timer, plus a little bit more, so just over 3 seconds by default. After the master downtimer, the master router can be assumed dead, and the backup router will take on the role of master. Just like before, the new master will announce himself to the network. One last note on VRRP. If the master router comes back to life, it will take over as the master once again. Okay, one last protocol I want to talk about. After VRRP was released, Cisco created a new protocol. This is called Gateway Load Balancing Protocol. Because this protocol was designed by Cisco, it has quite a few similarities to HSRP, but with some notable differences. Just like HSRP, each router will send a hello message to communicate with each other. The messages are sent every 3 seconds by default and are sent to a multicast address of 224.0.0.102. The routers will then choose which one will become the active router. How they choose an active router is the same as HSRP. The router with the highest priority, and if that ties, the router with the highest assigned IP address. Just like before, GLBP uses a virtual IP address. However, it does something different with the virtual MAC addresses. Instead of having one virtual MAC address shared between the routers, GLBP assigns a virtual MAC address to each router, and there is a very good reason for that. First though, let's look at the virtual MAC format. The first part represents the GLBP virtual MAC address. The yellow X's show the group number, and the red Ys represents something called the AVF ID. AVF, or Active Virtual Forwarders, are routers that have been assigned virtual MAC addresses. Just think of AVF as the router ID. So why does it assign different virtual MAC addresses to each router? Well, this is where the magic happens. Even though each host has the same default gateway IP address assigned, the routers can respond with different MAC addresses. This means both routers can be used to load balance the traffic rather than having only one active router and one standby router. For example, our host on the left has a default gateway of 192.168.0.254. It also has the MAC address of the active router, so all traffic will go through that active router. The host on the right also has the default gateway of 192.168.0.254, but this time it has the MAC address of the standby router, so all traffic will go through the standby router. By using different MAC addresses, we get the benefit of using both routers. Okay, let's move on. As we saw earlier, multicast hello messages are sent every 3 seconds by default. If our active router fails, then there is a hold timer which is 10 seconds by default. Once the active router is assumed dead, the standby router will take over and also take ownership of the virtual MAC addresses. When the old router comes back up, it will assume the role of standby, but it will take back responsibility for its own virtual MAC addresses. Keep in mind this is a high-level overview of these protocols. The CCNA does not require you to be an expert in any of these, but hopefully this has given you a good understanding. To summarize the key points, take a look at this table. The first column shows us if the protocol is Cisco proprietary or an open standard. The second column shows us the terminology used to describe the router roles. Next, it shows the multicast address used by each protocol. Then it shows the different MAC address formats, and finally, the number of virtual MAC addresses that can be used. I recommend learning this table for the CCNA. If you get any questions on this, this should hopefully cover it. This video is part of the full CCNA course which can be found in the description, so please feel free to go and check that out. That's it for first hop redundancy protocols. If you liked this video, don't forget to give it a thumbs up, leave a comment and subscribe. The support from you guys really helps this channel grow. Other than that, thank you for watching.
Hey, what's up guys? Welcome to Cert Bros. In this video, we're going to be talking about EtherChannels. If you've seen the STP video, you might recognize this diagram. What we have here is 3 redundant switches. They're redundant because if any one switch or cable fails, the other 2 can still communicate. We can take this redundancy further though. Instead of just having one cable between switches, we can have multiple. But as you can probably imagine, this brings another set of challenges. Let's zoom in on the bottom 2 switches so I can show you what I mean. Okay, so assuming you are familiar with STP, you'll know that we essentially have a switching loop here. So STP, doing what it does best, will block one of these ports. But this isn't what we want. We want to take full advantage of our extra cables and extra bandwidth. So what we can do instead is group the ports together on each switch. This is an EtherChannel. The EtherChannel creates its own logical interface, and STP will put this interface into the forwarding state. Now we can take full advantage of the extra cable and the extra bandwidth that comes with it. EtherChannels will even load balance over each cable. So now our 100 megabit Ethernet cable has become a 200 megabit Ethernet cable. And if one cable is pulled out or it fails, no problem. EtherChannels will just keep using the remaining cables. This stops STP from needing to reconverge anytime a cable fails or is pulled out. Once you find your way down the hall and to the rack, you can replace the cable and everything is back to full speed again. Okay, so some points on ether channels. They act as one logical interface. This allows traffic to keep flowing even when a cable is unavailable. It's also a way to avoid sending the same data back down the other cable and causing a loop. This is because a switch will not send data back through the same interface it received it on. We only have 2 cables here, but you can have up to 8 parallel cables in one ether channel. There are 3 methods to configuring ether channels. You can manually set it, or you could use either PAGP or LACP to negotiate whether or not to join an ether channel. Now, it's recommended to use negotiation rather than statically assigning it. This way you avoid any misconfiguration. And as you've already seen, ether channels will load balance the traffic. There are some requirements for ether channels to work. You will need to make sure that all ports in the ether channel has the same duplex. These days it's usually full. Speed. So you couldn't have some ports running at 100 megabit and then some running at 1 gigabit. That just wouldn't work. They all need to be either an access port or a trunk port. You would usually be doing this on trunk ports. It's worth noting, if you do use an access port, they need to be on the same VLAN. If you use trunk ports, they need to have the same allowed VLANs and the same native VLAN. You also need the same STP interface settings, such as port priority. I mentioned there are 3 choices when configuring ether channels. You can either set it manually, or use either Link Aggregation Control Protocol, LACP, or Port Aggregation Protocol, PAGP, to negotiate the ether channel. The reason it's recommended to use negotiation rather than setting it manually is because you run the risk of misconfiguration, which could end up with one side using ether channels and the other side not. This means that data could, in theory, be sent from one switch, and then the other side could send it back on the other port. In very specific situations, you could end up with a switching loop. And if you've seen the STP video, we all know what switching loops do to your network. The better option is to use either the Cisco proprietary protocol, PAGP, or the IEEE standard LACP to negotiate whether or not to become an ether channel. When configuring ether channels on the switch, you will need to remember the keywords and what they mean. On both sides of the cable, you will need to match these keywords with the protocol you are trying to use. So if you use the on keyword, this will statically set the ether channel. Desirable is the proactive option for PAGP. It will reach out to the other side and say, hey, want to join my PAGP ether channel? Desirable auto. Auto is the passive option for PAGP. It will respond to desirable port messages, but it won't put in the work. If you have an auto configuration, both ports will just not speak to each other and no ether channel will form. Active. So active is the proactive option for LACP. This is the same as desirable for PAGP. Again, it will reach out to the other side and try and form an ether channel. Lastly, active-passive. Passive for LACP is the same as auto for PAGP. It will respond to active port messages, but it won't proactively try and form an ether channel. So you can't have 2 passive ports or an ether channel just will not form. So we'll go through a quick config demo. But before we start though, you're going to see the terms channel group, port channel, and ether channel. It can be a bit confusing at first, but just think of all 3 as the same thing. I'll open up my first switch. Enable. Configure terminal.
And I'll use the interface range command to select fast Ethernet 0, 1 and 2. So the command we're going to use is channel group 1, which is the number of the EtherChannel we're creating. This number needs to be the same on the local switch, but can be completely different on the neighbor switch. Then we'll type mode, and if I do the question mark command, we can see the options we looked at earlier. For this example, I'm going to use the active mode and create an LACP EtherChannel. That's it for this switch. I'll open up the neighbor. And we'll do the same. Enable. Configure terminal. Select the interfaces using the range command. And again, I'll type the command channel group 1 mode active. So I could have used a different channel number, and I could also have used the passive mode command instead, and it would have still worked. We should now see our new EtherChannel come up. Cisco will call this a port channel. There it is, our port channel is now up. I'll exit out of here. And now run a show IP interface brief command. You'll see here way at the bottom that we have a new port channel interface. This is our logical EtherChannel. I can also run a show spanning tree VLAN 1 command. And we can see that STP is using the single port channel interface that is actually using 2 cables, and has put it into a forwarding state. Another good show command is the show EtherChannels summary. This will show us the port channel and which ports belong to it. It also has some flags at the top which will tell us the state each port is in. Using this, we can see that our port channel is a layer 2, and also it is in use. Both our fast Ethernet ports are bundled in with a port channel. If there's been some sort of misconfiguration, you may see the D flag, meaning it's down. You can even run a show interfaces port channel 1 command to see all of the information about this logical interface. You may note here that the bandwidth shows 200 megabit, which is 2 times our 100 megabit cables. The configuration really is that easy. The challenge comes when you've configured it and it doesn't work. This is usually down to some kind of misconfiguration. In this case, what you would do is first check the right modes have been used, then double check the requirements to make sure everything matches. That's it for EtherChannels. As always, if you've liked this video, then let us know by liking, leaving a comment and subscribing. The feedback from you really is what keeps the videos coming. Thank you for watching.
Welcome to CertPros. In this video, we're going to be looking at 4 network devices. These are hubs, bridges, routers, and switches. Okay, first we'll look at a simple hub. A hub's job is to connect devices in your network together. Let's see how it works. Let's say host A sends some data to host C. When a hub receives the data, it repeats it out of every port except the receiving one. Host C gets the data, but so does host B and D, so they simply discard it. The hub has many downfalls. It wastes bandwidth, as we've seen when host B and D receives unwanted data. A hub uses something called half duplex, which means it can't send and receive data at the same time without causing a data collision. This would cause your data to become corrupt and need to be sent again. So in overview, a hub is a layer 1 device, meaning it has no knowledge of addresses. All it does is repeat any data it receives. They have one collision domain and uses half duplex. This means it can't receive data and receive data at the same time. They waste bandwidth by sending data to hosts unnecessarily. It has security risks because all the hosts receive everyone's data. A malicious user could steal this. Hubs are old technology. They have now been replaced by switches, which we will take a look at shortly. Bridges were introduced to combat some of the shortcomings of hubs. They're used to segment networks into smaller sections. When data reaches the bridge, it decides whether or not to forward the data. It does this by looking at the destination and source MAC address. Every time the bridge receives data, it learns the source address, looks at the destination address, and decides to send the data or discard the data. We will look at this process in more depth when we discuss switches next, as it uses a similar process. So, a bridge is a layer 2 device. This means it can understand and learn MAC addresses. It segments LANs into smaller sections. It has 2 collision domains. This means data can be sent or received on each section of the network at the same time. A bridge usually has 2 ports. Bridges are not used anymore. They have also been replaced by switches. Now let's take a look at switches. Think of a switch as a hub and bridge rolled into one. It connects the devices together, but it can also learn which ports connect to which hosts. Let's see how this works. A switch has something called a MAC address table. This table will list each MAC address and which port is connected to. In this example, host A will send some data to host C. The switch receives the data, but as you can see, the MAC address table is empty. The switch in this case will forward the data out of each port just like a hub. Unlike a hub, the switch now learns host A's MAC address can be reached on port 1. When host C sends data back to host A, the switch knows exactly where to send the data. Now if you notice, the switch has learned that host C's MAC address can be found on port 3. Using this process, very quickly a switch can learn how to reach each host connected to it. Let's review. A switch is a layer 2 device. Like the bridge, it can learn MAC addresses, which are known as layer 2 addresses. A switch can use full duplex, meaning it can send and receive data at the same time. This means each port has its own collision domain. This is a huge improvement over a hub. Because it can learn MAC addresses, a switch saves huge amounts of bandwidth. And now because only the destination host is receiving the data, other hosts can't steal it. Routers. You can think of routers as the doorway out of your internal network and into the outside world. To understand what routers do, let's take a familiar example. Let's say this is your home computer, this is your switch, and this is your router. Now just on a side note, usually a home router has the switch built in, but in an enterprise network, they're separate devices. So on the other side of the router, you have the internet. Let's say you send an email or visit a website. Your computer will send data to the router using its IP address. The router will then forward the traffic out of your home network and into the wonderful world of the internet. When data comes back, the router will forward the data back to your computer. A router is the way out of your internal network. A router uses not only MAC addresses, but also IP addresses, which means a router is a layer 3 device, because IP addresses are known as layer 3 addresses. It usually has 2 ports. A router is highly configurable and has many different features that are beyond the scope of this video. That's it for basic network devices. You've learned about the older hubs and bridges, and also the modern standard of switches and routers. I hope you've enjoyed this video. If you did, don't forget to subscribe, leave a comment, and give a thumbs up. Thank you for watching.